All right. Okay. So we are starting. We are starting with the tutorial 1. Okay. Problem set 1. We said assume the following data. So we have Johnson. Sorry. We have this is our returns. This is our volatility, and we have J and J. With expected return of 7% and volatility 16%, and that of Walgreen is 10%. 10% and 20% here. Okay, so the first question is we know that the correlation between the two is 0.22. Now we've been asked to calculate the expected return and volatility of the portfolio that is equally invested in Johnson & Johnson and Walgreens. That means the share of J, so I can say X of J is equals to X of W, which is equals to 0.5. I hope it's okay. You can all see.
Yes.
Okay, great. Okay, so first of all, we are looking for the expected return. Now the expected return formula is X of J multiplied by the return on J. Multiplied by the return on J plus X of W multiplied by the return on W. So this one gives you the expected return. So the S of J represents the weight of each of the assets. So S of J in this case equals 0.5. Multiplied by the return of J, which is 7%, plus X of W, which is also 0.5, multiplied by return on W, which is also 10%. That means we have 17 divided by 2. Sorry, come on. If somebody has calculated, you can equally check so that we can all be at the same page. So 17 divided by 2, which is 8.5. So expected return is equals to 8.5%. I hope this one is okay.
Can you make your handwriting more legible?
Oh, sorry.
Yes.
Okay.
Yes, you can.
Right.
You're crazy.
All right. Okay. With the subsequent ones, I'll be careful with that. But it's okay. So what we are looking for is expected return, right? Now we know that the share of SJ, J is equals to 0.5, and the share of W is also equals to 0.5. Then the expected return becomes SJ multiplied by the return of J, which is 0.5 multiplied by the 7% plus 0.5 multiplied by the 10%, and that gives you 17/2, which is 8.5%. This one is okay, right?
Yes.
Okay, great. Now the next thing that we are looking for is the variance or the volatility. So the variance. Now, if you remember what we did in stochastic, sorry, I think somebody wants to join. Oh, okay, sorry. Waiting room. I think somebody wants to join. All right, okay. So we are looking for the volatility now. So the formula is, now we have this in this form, so I can say variance of the return is equals to SJ squared multiplied by the variance of J plus XW squared multiplied by the variance of W plus 2 SD XW
I beg you, go do this thing.
covariance of
You read on your own.
W.
You read them on your
Okay.
own.
So this is what we are looking at now. Now we have the variance formula as this: SD squared multiplied by the variance of J plus XW squared multiplied by the variance of W plus 2SJ SW covariance of JW. It's okay. But if you can see, we were only given correlation. So once you've been given correlation, you have to find your covariance. And we already know the formula for finding that. Who again wants to join? Okay, I think some other, okay, 3 people also want to join. Let's see. Sorry.
Give me your internet was a big password. Sienna, guys, you got Uche, mute your audio, I beg. Mute your audio, Uche.
Okay.
Host, can you mute everybody?
Okay, let me check.
What did you tell them? Okay. Fuck.
Another person wants to join. Okay, come in.
Gladstone, you have to organize a Zoom meeting on how to mute the Zoom section while we're having a meeting. Maybe after the class.
Okay, I think everybody's now here, so we can continue. Okay, so we are now looking for the variance, and we know the correlation now. Okay, I'm coming. I can't even. New white card. Okay. So in the question we were given correlation, but we know that correlation is the same as what? Correlation is equals to covariance between 1 and 2. I think the problem is coming from my end. 1 and 2 over the standard deviation of 1, standard deviation of 2. I hope you all know this formula, right? I think the problem is coming from my end because I'm using my laptop and my iPad at the same time. Is it okay? I hope we all know this formula, right? The correlation formula, which is covariance between okay. Hello. So we have this formula. The correlation is equal to this. Oh, again. think I'm not going to accept any. Okay, so let's continue. I think we are 20 now, so it's okay. Let's continue. Okay, so this is the formula. Correlation equals to this. So then if you're looking for the covariance, then the covariance now becomes 1, 2 is equals to. Yeah, my laptop is already on mute. I don't know why. It's already on mute.
What do you need your laptop for?
Because I have everything on it that I will be reading from the questions and everything.
Then you don't need to join the Zoom meeting with your laptop.
No, I'm
Just
joining
join
the
with your
meeting
tab.
with my iPad.
Yeah, join with your iPad. Then leave the Zoom meeting on your laptop so you can use your laptop and it will not disturb us on the Zoom. Just use the Zoom on the iPad.
Okay, I get to your point now. All right. Okay, so maybe I'll have to leave. But then I use my laptop to host it. Then that means I'll have to end it and do it again.
Oh, your laptop is our host.
Yeah.
You are supposed to you have to leave again. You can only use the iPad as the host.
You can transfer the
I think I should be able
the
to
host.
transfer.
You can transfer the host to someone.
Yeah, I'm coming. Let me check. Host. Okay, yeah, I think host. No, I think I'm coming. So how do I transfer it, guys? Okay,
Why start you now money transfer?
Peter, you are not correct.
Hey, can't you just mute the one computer you're not using?
That one is already on mute.
Oh, damn. Okay.
I don't know whether the problem is coming from my end or somebody's end, but because I've seen that you've already mute your machines.
Yeah.
I don't know why I'm getting the feedback.
You are getting it because you have two devices on.
And this one is even
connected
my volume with that of my laptop is already 0.
No, but it still might be echo. It still might be.
You still get
Do you know what I mean? Like, can you mute that laptop? Even if the volume's 0, it still might echo.
Yeah, it's 0 now, but you still get the echo, right? Or it's okay?
No, it's okay now, yeah.
I think it's okay, then we can continue. I didn't, okay, for the sake, I'm continuing. All right, so we have covariance of 1, 2 is equals to correlation multiplied by standard deviation of 1, standard deviation of 2. Is okay? We have this now. So, and in the question, we know that correlation is equals to 0.22 multiplied by the standard deviation, which is 0.16 of the first one, and that of 0.2 for the second one. So when I multiply this, I have 0.22 times 0.16 times 0.2 times 0.2, which is equals to 0.22 times 0.16 times 0.2 is 0.00704. 1, 2, 3. Great. So this is what we are going to get for the correlation. Now let's come to the volatility. So the formula is this. So we know that it's the same as what Sj squared, and Sj is 0.5 squared multiplied by the Sj variance standard error, which standard deviation, which is 0.16 squared plus 0.5 squared multiplied by 0.2 squared plus 2 SD, which is 0.5 multiplied by XW 0.5 Now we know the correlation covariance in this case represents what we have here, which is 0.00704. I hope up to this point, are we all okay with it?
Yeah, we are okay.
Okay, great. All right. So now let's do the computation. I think somebody can also try with a calculator so that we will all be at the same page. 0.5 squared. 0.5 squared times 0.18 squared plus 0.5 squared times 0.2 squared plus 2 times 0.5 times 0.5 times 0.00704, which is this, then square root of the answer. So I think the standard error I got is 0.14, which is, I think, which is too small. 0.14. Can somebody also cross check with the laptop, with the calculator for us to see? 0.5 squared. Okay, that is the same as, so 14.7%. But somebody can also check with a calculator for us to see if you got the same thing.
Yeah, it's correct. That's the
It's
answer.
correct, right? It's 14.7, right?
Yeah.
Okay, great. All right, great. Okay, so that means we have this variance or the volatility and that of expected returns. So let's look at the B. Unless if you have any question, please you can ask before I proceed with the next one.
Yeah, sorry. I thought she did the 0.22 for the correlation instead of the 0.00704. I thought she put like
Yeah.
11% for the answer.
Please, can you repeat your question again?
I thought she got 4.
Okay, so this is what we did. This is the formula that we use for the variance. Is that okay? Xj squared plus the variance of j squared. Sj squared multiplied by the variance of j squared plus xw squared multiplied by the variance of w squared plus 2sj xw multiplied by the covariance of j and w. Is okay? And in this case, we were given correlation. And once you know your correlation, it's also easy to find your covariance from that. Now, because I'm looking for the covariance, in this case, I said, okay, then the correlation formula is the same as covariance of J and W, or in this case, I use asset 1 and asset 2, divided by the standard deviation of asset 1 and that of asset 2. And through that, I said, okay, covariance of 1, 2 is equals to correlation times standard error of the first one times the standard error of the second one. And that gave us 0.0704. So that means the 0.074 here represents the covariance of J and W, right? Now we are looking, the formula is Sj squared multiplied by the variance of J squared plus XW squared multiplied by the variance of W squared. So multiplied by the variance of W plus 2 times Sj XW and the covariance of J and W. And we now know that the covariance of JW is now 0.0704, which is what I have here. This one. And this is the weight for SD. This is the weight for XW. And this is the standard deviation or standard error of volatility. But because I'm looking for the square, I just square it. And this is the volatility of SW2. So you just square that part and you get final answer 0.1470.
Osei, I'm sorry. Instead of 0.18, it's 0.16.
It's 0. What?
the volatility formula, it's not 0.18 square, it's 0.16 square.
It's 0.16, right? Okay, okay, sorry. All right, sorry. Okay, that means this one becomes 0.16, right?
Yes.
All right, okay, 0.1. Okay, so then let me check again. Sorry, thank you. 0.5 squared times 0.16 squared plus 0.5 squared.
And it's 14.11.
You had what? 0.2 squared plus
14.11.
It's 14.11, right?
Yes.
Okay, that's fine. Okay, so that's 14.11%. Okay, so this represents what? The volatility of the portfolio. Is it okay?
I have an issue because there's a bit of discrepancy between yours and Anastasia's. Because in her formula, she's using SJ squared times volatility of J, XW squared, the same thing with you, 2 times XJ times XW times volatility of W and J times correlation between J and W.
Yeah,
So
and that is what I did.
Solved separately. The difference is where you solved separately for correlation, for where you got 0.00704, you used 0.02 directly. She didn't solve
I get your point. Okay, look at something here. Look at this one. In place of this, look at something. You see, when we are talking about covariance, we are talking about variance, right? You can only have the variance and covariance. Correlation doesn't come in. But just that we know that once you have your covariance, you can also get your correlation from it. So in the question, you've been given correlation. So what Anastasia did was to replace this SJ with that of P, standard of error 1, and the standard of error of 2. Right? That's what Anastasia did.
Yeah.
So she didn't explain to you why it is correlation 1, correlation 2. But what I've done here is just to write a formula for finding a variance.
Okay.
Which formula for finding every variance is, let's say you have this one. Hold on. I'm coming 1 minute. Let's say you have y equals to ax plus bz, and we ask you to find the variance of y. If you remember, we said in this case it's the same as what a squared variance of x, plus b squared variance of z plus 2ab covariance of x and z. So this is the formula. This is the covariance of x and z. But how you are going to write this equation or this formula always depend on what is given.
Okay.
And in the question, she gave correlation, right? Now, if you have correlation and you are not given a covariance, then you have to get your covariance from the correlation formula. So what Anastasia did, yeah?
In the formula for finding variance,
yeah,
the last variable, is it covariance or correlation?
It is covariance of that well that you're looking at. If it's x and y, covariance of x and y. But why Anastasia?
Because in our last semester foundation for finance, I think when we were to look for variance, it is to be multiplied by correlation and not covariance. So
no.
I think
Peter, the whole equation is what we substitute over there is the covariance, and we know that the correlation coefficient, the correlation is equal to the covariance divided by the standard deviation
exactly
A and B. So before you can get the covariance over there, what you have to do is to multiply the correlation by the standard deviation of A and B. And that is what Osei has already done.
Exactly, that's what I'm doing, because if you don't follow it this way, you might get lost along the line.
Yeah. So there are instances there are instances that they will give you the covariance directly.
Covariance, exactly, and you'll not be giving correlation.
Covariance. That is where you have to more like multiply the correlation by the standard deviations of the two in order to get a covariance.
Yeah, that is it. Peter, are you okay?
Okay.
Yeah. So exactly the same thing that I did here. You see, so the same thing. This is the formula. Variance of R equals to SD squared. This. And this is the covariance that we have, right? But because Anastasia gave you correlation, you would have to transform this to get out of this. And I just showed you this formula that, okay, now if you have this, Anastasia gave us correlation. The correlation formula is the same as covariance between the J and that of W multiplied by the standard error of J and the standard error of W, right? Now, if I multiply, this implies that covariance of J and W equals to P, in this case, which represents a correlation, times the standard error of a first one times the standard error of the second one is okay. Then I will replace, so it's because I'm just replacing this expression. So what Anastasia did was to replace this one into the formula, and then she had 2 SGXW correlation multiplied by standard error of 1, standard error of 2. So this is what Anastasia wrote, right? This one. So this expression here represents the covariance, which is what we've written here. Please, is it okay?
Yeah, clear.
So I can continue, right?
Also, me, I'm clear.
If anybody doesn't understand anything, please just voice it out so that we can address it before we move on. Because this is for 2 cases, and we are now going to look at the 3 cases. And in that case, we are going to do the covariance. So it's better you understand it from this point.
No, Kusei, what I suggest, you had already wrote the equation for the correlation, right?
Come again?
You already had wrote that equation of the correlation. It's like the covariance of the two standard deviations, right?
Mm-hmm. Mm-hmm.
So it is supposed to be clear. I don't believe so.
Yeah, maybe I can't say it's supposed to be clear. Possibly our understanding might be different. But if anybody is okay, then we can proceed to the second one.
Proceed.
Yeah. Okay, fine. Then let's continue. Okay. So the next one that we are looking at is it said B, if the correlation between Johnson and Johnson's and Walgreen increase or decrease, would the expected return of the portfolio rise or fall? So first, let's write the formula for expected return. Expected return is equals to SJ plus the variance of J plus XW, returns of, return of J plus SW and the return of W. This is the formula. Now you can see that in this formula, there's no way that we have correlation. So whatever happens to correlation has nothing to do with returns. That means we can say that change in correlation. Oh, why did I can't write to all? So we can say that, okay, correlation has no change on the return. Okay, so P has no change on the return. Now the next one is would the volatility rise or fall? So what's the formula for the volatility? Variance is equals to xj squared multiplied by the variance of j plus x w squared multiplied by the variance of w plus 2. Because we are talking about the correlation, now I'm going to write this as sj x w multiplied by the covariance becomes correlation multiplied by the standard error of 1, the standard error of 2. So what happens to this volatility when P here changes? Now, because now you have to assume that, okay, if the P is greater than 0, if the P is greater than 0, right? Now, if the P is greater than 0 and the P increases, then what it means that the volatility will also increase. Is it okay?
Yes.
Yeah, and if P is less than 0, that means if it is negative, then when it increases, it also decreases, right?
It is the correlation. It has to be between 1 and -1, right?
Yeah, if the correlation is greater than 0, that means it is positive.
Yeah, there is a positive correlation, and if it's
exactly
less than 0, it is negative correlation. So
it's
there's
negative.
no relation. Yeah.
Yeah.
Hey, I'm sorry. So what happens like from the 0.22 for the correlation, right? What happens if it goes from 0.22 to 0.44? Would the volatility decrease then, even if it's less than 1?
So great. Look at something now. We have correlation to be 0.22, right? 0.22. Now, what it means that if it increases to 0.44, right? That means the expression here, this expression here, is going to increase. Is okay?
Yeah.
So when this expression increases, it means the volatility is going to increase. That is why we said the essence of using the portfolio is that the two assets that you are trying to use should have a negative relationship, because when they have positive relationship, you end up what increasing your volatility.
Yeah.
Jason, is it okay?
Yes. Yep. Thank you, man. Got it.
All right. Okay. Okay. So we are looking at the C part. Plot the efficient frontiers when P is equal to 1, 0, and -1. Okay. So same thing. Let me clear this part. Okay, so we are looking at the C part. Now we have plot efficient frontiers when we have only two assets. So the first thing is what if you are trying to plot efficient frontiers, first you have to minimize your volatility. Is it okay? That's the first thing you're supposed to do, because our interest of going for portfolio is what just to minimize our error. So I can say that now the variance of the portfolio is equals to x j squared multiplied by the variance of j multiplied by the variance of j plus xw squared multiplied by the variance of w plus 2sj XW multiplied by the covariance of J and W. So this is the formula, right? So there are two ways of solving this. It's either first, you use the Lagrangian approach, or second, because you have two variables here, Sj and then Sw, right? And we know that when you sum up these shares, it should always be equal to 1. So you have Xw plus Sj equals to 1, right? Now I can just make Sj the subject and it's okay. Sj is equals to 1 minus Xw. Then I have this. Now once I get this, I can replace this into the portfolio variance function, which is variance of this is now equals to, I know that Sj is now what? 1 minus Xw squared. So it comes 1 minus Xw all squared multiplied by the variance of J plus Xw all squared variance of W plus 2. Sj is now 1 minus Xw into brackets Xw again multiplied by, now if you like, you can also expand this and say that the covariance between J and W is the same as correlation between J and this multiplied by the standard deviation of J and the standard deviation of W. Please, up to this point, are we all okay?
I just want to understand, you made it 1 minus the expected value for what? It's like getting the values of each one is like.
What I'm trying to do here is this. We are trying to minimize the portfolio variance. Is okay.
Okay.
Now we know that when you sum up the shares of each of the assets that you have, it should always be equal to 1, right? So that's what I have
to make the market portfolio. Yes.
Yeah, exactly. Should be equal to 1. So that's what I have. Xw plus Sj is equal to 1.
Okay.
Now I just want to make Sj the subject from this expression. Right. So I can say then Sj is equal to 1 minus Xw. Now when I do that, then I can call this one equation 2. It's okay. Now what I'm doing here is that I want to replace the equation 2 into that of the portfolio variance, which is, let's say, this equation 1, which is this one. Is okay.
Yeah.
Now I'm doing this so that I can have this portfolio variance formula in only one function. That is a function of Xw. Is okay. Now in doing so, that because here is Xj squared, and because I'm now saying that Sj is equal to 1 minus Xw, then it becomes, in place of Sj, I write 1 minus Xw squared.
Okay.
Multiplied by the variance of J plus Xw, which is already there, plus this is 2 Sj Xw multiplied by the covariance between J and W. Is okay. But because we are saying that Sj is now equals to 1 minus Xw, I just replace the Sj as 1 minus Xw multiplied by Xw. And as we already said that covariance between J and W is also equals to what? Correlation times
the correlation
the standard deviation of the two.
Yeah.
Great.
Yeah.
So that's what I've done here, right? Now, because our target is what? To minimize. Anytime you hear of minimize in mathematics, it means you differentiate the function with respect to the variable that you are looking for, which in this case is Sj. So I'm going to have differentiate the variance of the portfolio with respect to Sj, and then you set it equals to 0. Now, when you set it equal to 0, then you make the Sj the subject, Sw the subject.
You mean assuming it's equal to 0, right?
Come again?
You mean assume to that, make it as an assumption? Like.
No, this is not an assumption. That is what you always do. Anytime that you have this and you are trying to minimize.
Oh, yes.
You always differentiate with respect to the variable that you are interested in. And in this case, we've been able to write the portfolio variance as a function of only XW. You can see there's no more SJ in it.
Yes.
Right? So what I'm going to do now is to differentiate this respect to XW. Right? Now look at something. Let's look at the first component, which is the first component is this one. Is okay.
Okay.
Now, if I'm differentiating this respect to SW, this is into bracket and it has what? Exponent of 2, right? So the 2 will come down, then I'll have 2 into bracket 1 minus XW. Is okay. Then you subtract 1 from this one again. So that means the exponent will be only 1 here, right?
Yeah.
And once it is 1 in mathematics, there's no point in writing that. Right. Now, after you are done with that, then you differentiate what you also have in the bracket. Now, in the bracket, it's what? Minus XW. Is it okay?
Yeah.
So when I differentiate minus XW, I have what? Minus 1.
Yes.
So that means I can just bring minus here. So I have minus 2 into bracket, 1 minus SW. Then I'll bring my variance of J. Is it okay?
Yeah,
so
it will go down, yes. Yeah.
Right. Now let's come to the second component, which is this one. If I'm differentiating this respect to XW again, it comes 2 will come, right? It comes plus
2x.
2x W, then variance of W.
Of them.
I hope this part is very simple, right?
Yeah, yeah. Now it's
Great.
clear. It's more clear.
Great. Now, when you come to this part, let's look at this expression. If your mathematics is not good like myself, what you can do is first expand them. You can decide to expand it. It's okay. If I decide to expand this, I'm going to have 2xw. Already we know that this expression is equals to covariance between J and W, right?
Yeah.
Because there's no, I don't have my space, I'm going to write this as 2SW, then covariance between J and W minus, this comes 2 times SW minus 2XW squared. Then that will give you multiplied by the covariance between J and W. Is okay? So I've just tried to expand the third component of the equation that we are looking at. That is, if your mathematics is not good, but if your mathematics is good, you can just differentiate it straight away and then you get your answer. Is okay?
Okay.
So after I have expanded this part, I now have this to be what? In 2 equations, right? Now I'm differentiating this first expression with respect to XW. So when I differentiate that is going to give.
Hold on, please.
All right.
There's a little bit of confusion from the expression under the differentiation. How did you go up again?
This one?
Yes.
You mean this expression?
Yes. How did you realize that expression?
Okay. So first, we have 3 components of the equation that we are looking at. The first component is this one. Is okay?
Yeah.
The second component is this one. Is okay?
Yeah.
And the third component is this one, right?
Okay.
I'm looking at the first component. Now the first component, it is 1 minus XW all squared multiplied by the variance of J, right? Now, when you look at the question, the only thing that we do not know is XW, because the variance of J and W, it has been given already, right? So the one that I do not know, that's what I'm going to differentiate the portfolio variance with respect to. So what I don't know in this case is XW. Now, if I want to differentiate XW, I will differentiate this with respect to XW. Then in mathematics, because everything is in bracket, these two here, the exponent 2 here, it comes and that will give you 2 here, the 2 that I have here.
Yes.
Right? Now, then I'll subtract 1 from the exponent. So when I subtract 1 from the 2, I have 1. Is it okay?
Yes, I'm following you.
Yeah, so and in mathematics, any exponent 1, there's no point in bringing the exponent 1, right? Now, when I'm done with that, because it is in a bracket, I also have to come back to what is in the bracket. Now, in the bracket, I have minus XW. Now, when I differentiate with respect to, when I differentiate this with respect to W, I'm going to have only minus 1. Because there's minus XW.
Yeah.
Differentiate with respect to SW, I have minus 1, right?
Yeah.
And that is why I negated this one, meaning minus 1 times that will give you only the minus here.
Okay.
That's for the first part. Now, the second component is this one. Now, this I'm going to bring, if I want to differentiate with respect to XW, then the 2 will come down. That will give me 2XW.
Yeah.
Then when I subtract 1 from there, I have the 1. So there's no point in bringing the exponent 1. And I multiply by what I have here. So okay. we are done with the 2 components of the equation. Is it okay?
Okay, yeah.
Now let's move with the third component. Now with the third component, what is this one? What I'm saying is that if your mathematics is good, then you can easily differentiate it. There's no point in expanding it. But if your mathematics is not good and to save yourself, then expand it. So what I've done is this. You see, this is 2, right? 2 times 1 is what?
2.
2 times XW, and this will give me XW correlation between J and then W, right? Yeah. Sorry, the standard error between J and the W is okay. But because what I've done here is just to represent this expression with correlation between J and W, because I know that this expression represents correlation. And because I have just a small space, that is why I've used covariance between J and W to represent this expression here, right? Now, when I expand the other part, it becomes SW times SW, so SW squared. Multiply by 2, that will give you 2SW squared, but there's already a negative here. Yeah. And I multiply by the correlation between correlation times standard deviation of J times standard deviation of W, the same as the covariance of J and W. It's okay? Yeah. Right, so you have this. So what I've done here is just for the first 2 parts. Now I have expanded the second, the third equation, which has also given me 2 different equations, 2 different components. Now, if I want to differentiate this expression here with respect to SW, then that's going to give me 2, because it is this one is plus, so it's going to give me plus 2 covariance between J and W. Is it okay?
I see.
Yeah?
Yes, he said I'm quite confused on the expansion he did.
Sorry. Oh, no problem, no problem. Look at something. You see, let me take it. Okay, let me clear this part and write it again. All right. Let me clear everything here. Okay, so okay, so it was like this. Last one, it was like this: 2 into bracket, 2 into bracket, 1 minus XW, right? Multiply by SW, correlation, then standard error of 1, J, and then standard error of W. Glass, so this is the formula. This is what we have. Is okay?
Yes, okay, let's continue. Yeah.
Great. So look at something. Let me put, because everything's being multiplied, so this, let me bring these two out. It's okay. Because it is just, everything's being multiplied, so I can just bring the two out. Now, let's say I have this. So let this one also in bracket, like this. It's okay. Now, 1 times everything here is the same as 1 times that number, right? So I'll have 2. 1 times this gives me XW, correlation, standard error of J, standard error of W. It's okay. So I've just multiplied the 1 here by the expression here. It's okay. It's okay, Glassman.
Yeah.
Okay, great. Now then the second component is this one, minus XW. It's okay. Now minus XW times this is going to give me minus XW squared multiplied by the correlation, which is this standard error of J, standard error of W. Is okay?
Yes, boss.
Then you have 2x, multiply everything by 2. 2x, this correlation between this J, W, minus 2x W all squared. Correlation multiplied by the standard error of J, standard error of W. Is okay? So this is what we have now. Are you now okay?
Yes, I am.
Okay, please. So in case anybody does not understand the mathematics, you can also equally ask and we go back. Now, in this case, I have here. Now, what I'm interested in is to differentiate this expression with respect to XW, right? Because when you look at what we have here, the only thing that I do not know is the XW. I know my correlation, which is 0.22. I know my volatility for J, which is 0.16. I know my volatility for W, which is 0.2, right? So the one that I do not know, that's what I'm differentiating respect to. So when I differentiate this expression respect to XW, I'm going to have 2 correlation multiplied by the standard error of J, and then standard error of W minus. Now, when I come to the second component, which is this one, when I differentiate respect to XW, the 2 here will come here, making it 4 minus 4 XW correlation, this J, this W. Is okay?
Yes.
Great. Now, so let's look at the other component that we did, which was this one. I think, okay. So in this case, to this what we had minus 2 x1 minus this. There was the first part. This is what we had for this one. It was this one. So we had minus 2 and then variance of J squared. And the other one was minus 2 XW and then variance of W. Okay, so when I differentiated the first two components, which is this one, and this one, this is what I had: minus 2 into bracket 1 minus XW all squared multiplied by the variance of J. Then sorry, this one was plus 2XW multiplied by the variance of W. Is okay. So that means I'm going to add it onto this one. So I'm going to have minus 2. So this is going to give me minus 2 into bracket 1 minus XW multiplied by the variance of J plus the other one also plus 2 XW multiplied by the variance of W. Is okay. Now I said after you have differentiated, you set everything to 0. Please, is it okay? If you don't understand anything, please, you can ask.
It's okay.
It's okay. Great. All right. So we are here now. So what I'm coming to do now is let me expand this expression also. Let's expand this expression. So we are going to have 2 correlation of standard deviation of J, standard deviation of W, minus 4 SW minus, okay, so in order for things to be simple, let me replace, if you're okay, I'm going to replace this one with covariance between J and W. Is that okay for you guys?
Yes, they are the same, yes.
Yeah, they are the same. So let me, so that it will be quite easier for us. So we are going to have the first component becomes 2 covariance between J and W minus 4 X W covariance between J and W. Now when I expand this one, I'm going to have minus 2 variance of J, minus 2 variance of J, plus 2 XW variance of J, plus 2 XW variance of W equals to 0. So now we have it like this. So we can decide to divide all the terms by 2, 2, 2. Is it okay? So when I divide both terms by 2, 2, 2, I'm going to have this expression divided by 2, this expression divided by 2, this expression divided by 2, this divided by 2, and this one also divided by 2. Right? So now this one will be covariance between J and W minus 2 XW covariance between J and W minus, this one is variance minus 2 variance of J, right? This is minus 2. So this 2 becomes variance of J. And then this part becomes plus SJ plus SW variance of J plus XW variance of W equals to 0. Please, up to this one, is it okay with everybody?
Yes.
Okay, now from here, because we are interested in making XW the subject, now we can send those with XW in it to the left side of the equation. So that is going to give us, we can say, we are going to have first covariance of J W minus variance of J is equals to So let's look at it again. The last one is equals to, so we have it as, now when this one crosses the equal sign, look at something here. We have, so I've taken this one already. I've maintained this one here, this one here. Now when I send this one, it's going to give me -2. I'm sorry, let me take pen and write it here. So when I send, so I'm maintaining the first two, which is covariance between J and W. This one here, I'm maintaining it minus the variance of J is equals to. Now, if I send this expression here to the other side of the equal sign, it's going to be positive, right? So that is going to give me equals to 2xw jw. And then when I send this also, this expression also to the other side of the equation, it is going to give me what? Minus, right? So that is going to give me minus SW variance of J minus SW the variance of W. So that is, so that means I'm going to have it as so I'm going to have this now as okay. So I think it will better I use the product sheet. Okay, so let me use what the T did so that you will all understand. Okay, so let's rather maintain this one here. Come in. Okay, where's the last one? Sorry, so where's the last formula that I wrote? Sorry, this one. Okay, so what I'm trying to do now is this. So when I'm now going to have variance of covariance of JW minus variance of J is equals to 2xW this JW minus xj minus xw variance of J minus xw variance of W. Please, this one we have, but in the case of Anastasia's own, she rather send this on the other side. So what we can do now is we have this, but in order to get what Anastasia got, we should have maintained this here. We should have maintained this one here and then send this one also to this point. So that's what I'm going to do. Is it okay? It seems please, are you guys following?
Yeah, continue.
Yeah, so what I did here is this. You know, in the case of Anastasia, she rather maintained the ones with the XW on the left side of the equal sign and sent the other ones to the right side of the equal sign, which I did the reverse. So I want to do what Anastasia did so that we can arrive at the same answer, so that at least everybody will be okay, right? So it's the same as just writing that, okay, now if I want to send this one here, the ones here to the other side of the equation, that is going to give me, when this one goes, the variance of J goes, the other becomes positive variance of J. Now when this one also goes, the left side of the equation becomes minus covariance of JW. So I'll bring my equals to here. Now let me also send these ones here. So I'm going to have XW variance of J plus XW variance of W minus, so minus 2XW covariance between J and W, right? So the common term is XW, so I can just factor out XW and see that the XW is the same as variance of J plus variance of W minus 2 covariance of J W equals to variance of J minus covariance between J and W. So I will divide those side by this part. Variance of J plus variance of W minus 2 covariance of J W. So the same thing, variance of J plus variance of W minus 2 covariance of J W. That means this cancels this one. Then I'll have my XW as equals to variance of J minus covariance between J and W all over variance of J plus variance of W minus 2 covariance of J and W. Is okay? So this becomes the minimum weight. That is when you minimize the weight that you're going to have for SW. So if I'm looking for SD, then you said SD is also equals to what? 1 minus XW in this case. Is it okay? Please, so this is the final answer for finding the SW, which is to say we've now gotten SW now. Now we are now going to look for SD. But up to this point, are we all okay?
Yeah.
We are okay, right? Okay, great. So now if I have FW is equals to variance of J minus the covariance between J and W all over variance of J plus variance of W minus 2 covariance of JW. Great. So then the question was plot efficient frontiers when correlation is equal to 1, 0, and -1. Great. Now, so let's go to the next page. So what I can say, yeah.
But when we have like 3 stocks as we have in the bonus exam, should we use the same, not the same, but something like this formula or another one?
With when you have more than 3 stocks, I'm going to explain how to use X out. I'll explain how to derive the metrics thing that she did and how to solve using the Excel, because if you have more than 3 and you want to minimize, it's going to be difficult for you solving it within the 15 or 10 that she wants you to use. So the easiest way is to use the metrics.
Okay.
Yeah. So when we get there to, I'm going to explain that, and we can as well also use metrics to solve for the 2 cases, which is very simple. But I want to follow what she did so that you guys will understand up to what she has done in the notes.
We'll do this today or another time?
Yeah, we are going to do that today.
Okay.
We are going to do that today. Yeah. So up to this point, we are well. So let's finish this one, and we might even look at the 3 cases, which is problem set 2. So let's finish this one. All right. So now that is what we have here. So we've gotten this. Okay. So we've been asked to plot when correlation is equal to 1 0 and -1. It's okay. Now, when you check the formula that we got, which is XW is equals to variance of J. Now, we know the variance of J, right? Equal to the variance of J minus the first one, covariance of what? J and W. But we know the covariance of J and W is also P correlation multiplied by the variance of standard error of J, standard error of W, all over variance of J plus variance of W minus 2 covariance of J, W is then minus 2 correlation multiplied by J and W. Is okay? Up to this one is okay, right? What I've done here is just to replace the covariance that we had with correlation times standard deviation of J times standard deviation of W. Because in the question, you've been given correlation. So if you don't replace that formula with a correlation formula, it will be difficult to solve it. Is okay?
Yes, clear.
All right. So the case when when correlation is equal to 1, I'm going to have XW is equals to variance of J. Now we have volatility of J to be what? 0.16. 0.16 all squared minus correlation is 1 times, okay, minus correlation is 1 times the standard deviation of J, which is 0.16, times that of standard deviation of J, W, which is 0.2, all over the variance of J, which is 0.16 squared plus variance of W, which is 0.20 all squared minus 2 times of 1 times 0.16 times 0.2. All right, so let me do it. Okay, so 0.16. So we're going to have 0.16 squared. So somebody can also cross-check with their calculator, please. 1 times 0.16 times 0.2, bracket close, 0.16 squared plus 0.2 squared minus 2 into brackets 1 times 0.16 times 0.2. Okay, so I had, yeah, SW equals to -4. Now when SW equals to -4, then we can say that then SG is equals to what? 1 minus XW, which is the same as what? 1 minus -4, which equals to 5, right? And we said that the sum of the weights should be equal to what? 1. So XG plus XW is equals to 1. That means SG 5 plus 5 minus 4 is also equals to 1, which is correct. But if you remember, when you work her tutorial, when you go to that point, I think she used a positive correlation different from 1. Please, up to this point is okay, so I can continue, right?
It's okay, but the numbers I didn't follow that, to be honest. But I know it. It's I understand it now. Yes.
It looks like she used 1 too. XW is equal to 1 minus XJ.
Yeah.
That's what she used.
So, but up to this point is okay.
Yes.
If there's something you don't understand up to this point, please you can ask. It seems like only some few people are talking here. Richard is not talking. Fuller is not talking. Gladstone talking.
I said yes, man.
Peter.
Calling them out.
Yeah, I think I got lost.
I think what we are doing
Up to this point is okay, right? Up to this point is okay.
I think Richard, he was saying that he's lost.
Is lost.
Yeah, I think I got lost in between, but maybe you can continue.
Oh, but no, then you are not being fair. When you get lost, just draw our attention, because that's the essence of the discussion here. So if you spend 1 hour, 2 hours saying that you don't understand anything, then what's the relevance of you being here? That's why I kept asking. If there's something you don't understand, just point out. Because this is 2 cases. After here, we are now going to do the 3 cases, which is even my target for today. Right? That is even my target for today. So if you don't understand the 2 cases and you're asking me to proceed, then how would you understand the 3 cases?
So maybe you can re-explain. I got to the part where you're expanding the bracket, but I think afterwards I don't know, maybe I got lost there. I got to the part that you are expanding the equation with 2 minus, when you differentiated the equation.
Okay, you don't worry. I'll sort you later. But with the subsequent ones, if there's something you don't understand, please just draw my attention to it.
Sure.
Yeah, but before you do this, can I ask a question, Jose?
Sure.
In here in the page, the current page right now, XW equal whatsoever you wrote, okay?
This one, I'm coming.
No, the one that we were, the last.
Let me look for it. I'm coming. Oh, where is this? Not this one. This one. I think not this one.
The one that we were just working on it, right?
Yeah. I think that's what I'm looking for, and I don't even.
Which is the XW standard deviation.
Okay, this one is this one. This one.
No. The after.
This is the current one.
This one, yes, the current.
Yeah.
This one. So
yeah.
Why cannot we, in the case of 2 stocks, we only use this equation right away? I mean, we don't have to go right through all of that.
You said yeah. So yes, you don't need. I think she did this just for people to understand what was going on.
Yeah, right.
But if you don't minimize and solve, well, if you can memorize the formula,
I think the minimization.
It's up to you, fine.
Yeah, but what I'm saying is. Yeah, but what I'm saying is the minimization will be required on the 3 stocks and forward. That's what I think. I'm not sure, you know.
You said 3 stocks also require what?
The minimization will be required in the three stocks of a portfolio of 3 stocks and more.
Mm-hmm.
But in 2 stocks, you can only implement, because there's nothing is going to change. There will be the same equation. I mean, this XW, it will be the same always.
Yeah, that's true.
Right? Okay, that's good to know.
That's true. So for the 2 cases, fine. It's not a big deal. And then I think most people have issue with the 3 cases, which is what we're going to look at. That's the most important one. Is it okay?
Yeah. Okay. Sorry. Thanks.
Right. Okay. So now once you get this, the next one is what? Plot the efficient frontiers. So let's go back to what we did again. Now in the question we said J and J had a return of 7%, and volatility of 16%, and Walgreen also had 10%, and volatility of 20% here, right? Okay, so now we know that XJ, which represents the weight, SJ was 5. I think SJ was what, 5? SJ was 5. Sorry, SJ was 5. sorry, this one was 5, and this one was -4. I hope I'm correct. That's what we got, right?
Yeah, yeah.
Great. So if you are looking for, if you are going to plot it first, you can decide to plot the first one here. Let's say this is our variance, and this is our mean here. So the first one is J and J, which is 16, and the return is 7. So we are here. Now, and the next one is 20 and 10. Let's say 10 is here. So that one will also be somewhere here. So when I plot, I have this for this one and this. So now the next one is to locate the minimum, the MVP points, minimum variance portfolio. All right. So now we know that the minimum weights are what? 5 and -4. So then expected return at that point becomes 5 multiplied by 0.07 or 7% minus 4 multiplied by 0.1, which is 10%. So I can say the same as 5 into brackets 7% minus 4 into brackets 10%, which is no, that will give you negative, or 5 times 7. I'm sorry. Okay, so 5 times 7 will give you 5 times 7 will give you 35. Yeah, that will give you 35 minus 4 times 10 will give you 40. That means it's supposed to be negative. But if you remember, when she was solving this in the tutorial, I think she didn't use the p equals to positive 1. She used a different positive number correlation. I don't know if anybody has watched her video.
Yeah, the initial correlation she gave, like, I think it was 0.2.
It was 0.22,
yeah.
Right? But when you look at the C part, she said plot efficient frontiers when P is equal to 1, 0, and -1, the C part, right? But when she solved for the minimization problem and she got her SJ and then SW, she didn't solve. She didn't use the case when P was equal 0. Equals 1. She rather used 0.2 to do that part. I don't know if somebody has seen that too.
Yeah.
I saw, but I don't remember exactly, to be honest.
Yeah. I noticed that it is because I'm sure possibly she realized that when you solve using the 1, you are going to get something like this. Because at the end of the day, you have negative return. That is not possible.
Exactly. That is why she chose the 0.2.
What I remember, she didn't solve 1, right? I think she didn't solve 1 out of them.
Yes, she didn't solve for the case when correlation equals to 1, but she used 0.22. And I'm sure the reason was because of this. But please, up to this point is okay, right? So imagine after solving for this, let's say we would have gotten something like, let's say 9%, right? Let's say we would have gotten something like 9%. Then we solve for the standard L2, we get something like, let's say 18%. Let's say we solve and we get something like, say 18%. It's okay. Then I'll just come and plot this. The 9% will be here, and then the 18% will be in between this. So that means when they are going to be around this, then I'll just join it like this. Then this becomes the efficient frontier. So from this point up to this point becomes the efficient frontier. Is it okay?
Yeah.
All right. So if this is okay, then I'm going to skip the D part because the D part is almost the same as that of the first one that we did. Because she says calculate expected return and the volatility of the portfolio that consists of a long position of 10,000 in J and J and short position of 2000 in wall green. Okay, fine. So let's go. Let me do that right away from here. Okay.
Can we proceed with this matrix?
Yeah, that's
the same for the
so
quantities.
I can skip this one, right?
Yeah,
Yeah,
because this is the one that I'm really confused about. I forget actually how to make the matrix.
No problem.
Yeah, thanks, bro.
Okay, so with the three case area, let's look at problem set 2, because that is going to help us to do that one. Okay, so he says you have stock H. You have stock H. And that's a return, and then volatility. So stock H has a return of what, 20%, and a volatility of 30%. Is okay. And but you plan to invest a total of 50,000, okay, in raising what have you, all right. So let's say, and both K and L has 10, 20, 10, 20. Okay. So I'm going to skip the first part, the A part, because that is a true case scenario. And look at the third one. Now suppose the correlation between stock K and L. So let's have our correlation matrix here. Let's have our correlation matrix. So I'll call this H, K, and L. H, K, and L. Now, so correlation between H, so it says if K has a correlation of 0.5 with H, so K and H is 0.5 positive. It's okay. So the same here, 0.5 positive. And L has a correlation of negative 0.5 with H. L and then H has a negative 0.5. Negative 0.5. Oh, why? Okay, negative 0.5. So correlation between H and H is 1. K and K is 1. L and L is 1. So he says, and then, so H and K is 0.5, 0.5, right? So this is H and H is 1. This K and K is 1. So we said H and K is 0.5. That means K and H at the same time is 0.5. And it says K and L, sorry, H and L. So K and L is also 0. K and L. K and L is 0 here. And then that means L and K is also 0. And this one is negative 0.5. Please, I hope we all understand this correlation matrix table, right?
How do you know K now are 0?
Because in the question it said, suppose the correlation between stock K and L is 0.
Okay.
So I'm only plugging the correlation between each stock together, right? In the matrix.
Come again?
I plug in the correlation values of each stock and the relevant one, right?
Mm-hmm.
So H and H, what is the H and H is a covariance. It will be a variance, and then I'm only blocking the correlation, right?
this correlation matrix is different from variance covariance matrix.
Yeah, but we have still the variance is 1 in each. I mean, variance for each one.
Yeah, the variance.
The covariance for each one.
No, that is not variance. That is correlation. Correlation between a variable and itself is 1.
Yeah, exactly.
But it's not the covariance.
Yeah. Okay, so this is a correlation between each stock and the other.
This is a correlation matrix.
Okay.
Correlation is different from covariance, variance covariance matrix. They are not the same thing.
Okay.
Yeah, great. Okay, now this is what we have. Now the question is, suppose how much money you have to invest in each of the stock A, K, and L, right? So first of all, we have 3 assets, right? So we have stock A, B, and C. So let me draw this again, then I'll form my portfolio from it. We have, now I'm going to do the variance covariance matrix. Okay, so let me call this part E. Okay, let me call this part K, H, K, and L. H, K, and L, right? Now this becomes the variance of H, right? This becomes the variance of K, because it's K, K, and itself.
I'll say sorry, but when we multiply with it by 2, when we do the variance covariance matrix, in which case we multiply this by 2?
No, that is only when she's trying to minimize and she differentiates. That's when the 2 comes in. So when I get that, you know how it comes in, but it doesn't come in yet.
But here we don't need to minimize.
We have to minimize, but what I'm trying to do now is to set up the portfolio equation before you can even think of minimizing. Because if you don't know the portfolio formula, how are you going to minimize?
Okay.
Do you understand my point?
So we're trying to set up the correlation between all the stocks in the portfolio, right?
What I'm trying to do right now is just to write my variance covariance matrix.
Yeah, I know that, but for what?
Yeah, that's what I'm trying to do. Yeah. So what I'm saying that this becomes variance of K. It becomes the variance of L. So this can have covariance between H and K. Then we have the covariance between H and L. Then we can become covariance between H and K. And this one becomes H and L. H and L. And this one becomes covariance between K and L. It's okay. Now, so after here, what we are going to do here is just to sum everything here. I'm going to sum everything.
The last one in
which one? Okay, sorry. That is what covariance between K and L, right? Okay, so I'm going to sum everything that I have in this matrix, and that will give me the variance of the portfolio. So the variance of the portfolio is equals to, first, let me sum the leading diagonal, which is going to give me variance of. So when I try to do this, so now we have this one here. So when I want to do this, oh, sorry. So when we have the other assets, so I'm going to have the equals to variance of the portfolio is equals to the weight of H, right, all squared, multiplied by the variance of H. which is this one, is okay, plus the weight of K all squared multiplied by the variance of K plus the weight of L all squared multiplied by the variance of L, which is, so I've added these ones, plus 2, yeah?
I'm not seeing what you're doing.
Come again?
I'm not seeing what you're doing. Can you write it somewhere else? I don't know.
Oh, all right, sorry, okay, all right, okay, so let me come here, okay, let me go to a new page. All right, so what I'm doing now is I'm trying to form the variance, portfolio variance for the 3 cases. So the same as X, K, all squared multiplied by the variance of K plus XH all squared multiplied by the variance of H plus XL all squared multiplied by the variance of L plus 2x, now look at that, plus 2xh XL multiplied by the covariance of H and L, right? And this, I'm getting this expression here from here. This is from here. Look at something. If I'm looking at here, I got SA squared multiplied by what? Variance of A squared, because this is H, right? The H here.
What line
There's
are
another
you
H.
Which column are you talking about?
Come again?
Like you're just talking, we don't know exactly where you're talking about. Can you just touch so we know where you are?
I was here. I was here. I'm writing the variance formula. Is it okay? So I've done this. Now I'm explaining how I got these ones from the metric that I drew. So basically, whatever. So it's the same as plus 2 x h x k multiplied by the covariance between h and k plus 2. So it's left with L. I have HL. I have HK. It's left with what? It's left with what? KL. So plus SK XL covariance between K and L. So this is the formula for the variance. Is okay. Now what I was trying, so this formula I was trying to explain how I got this from this. So in this case, this is H, right? And it's moving with this one. So it comes A times H is A squared, multiplied by the variance becomes A squared multiplied by the variance squared, right? Now when I look at this, H and K, it becomes HK, which is HK, right? It becomes HK. Now multiply by, but HK appears twice. So it comes covariance of HK plus covariance of KH, which is this one. So this and this gives you 2. So that is also giving you this one. That is also giving you the 2 times the covariance that appear twice and times SH and SL. But if you are, once you are able to write this one, you don't need, I'm just trying to explain for you to understand how I was deriving these things. But if you can derive this one, it's not very, very, very important. But the most important thing is being able to write this one. This is a variance for 3 cases, in the case that you have 3 different assets.
Okay, I have a question, please.
All right.
Why are we looking for the variance?
No, because in this case, the question is what? Suppose the correlation between stock K8 and 0, you want to invest a total of 25. How much will you invest in each stock to achieve a minimum variance portfolio? It's okay. So to achieve a minimum variance portfolio, the question is always minimize the variance subject to your summation of your x, that your weight equals to 1, and the mean of the portfolio is equals to summation of xi multiplied by the return on I. It's okay. So the question is minimize variance of the portfolio subject to your weight, which is sum up to equals to 1. And when you're also giving portfolio return constraint, like the one that we had in the bonus exams, it's okay. Now, if you have something like this, now the question is, you are saying that minimize your variance, but what is your variance? You are supposed to know your variance. And that's what I'm writing here. So this is a variance. Is okay?
Yeah, it's clear. Thank you.
Yeah. So that's what I'm trying to. Now, once I know this, then the question is minimize. But in this case, in the question that we were looking at, we were not giving any portfolio return. That is, they didn't state that they expect us to have a portfolio return of, let's say, 20% or 10%, just unlike the one that we had in the bonus exams. That they also specified that they're supposed to have this portfolio return. I don't know if you remember.
Yes.
But in our case, there's nothing like that. So then the only constraint that we are going to have in this case will be only this one, subject to the portfolio weight. It's okay.
Yeah.
So what I'm now coming to do is to set up a Lagrangian function. So let me clear this one so that I have some space. Okay. So what I'm coming to do now is to set up a Lagrangian function, which is equals to the variance of the portfolio is okay, plus lambda into bracket 1 minus s of h minus s of l minus s of k, because this one represents the constraint. Now I'm writing the variance of portfolio, which means it represents everything that I have here. It's okay. I'm writing the variance of just to represent everything that I have here.
Okay.
Yeah, because I don't have space to write.
This is a quick question. Like if xah plus xl and plus xk, it's 1. If we subtract from 1 all of this, how it works?
It is just like when you were doing the microeconomics that you have your utility function, and they give you your income that you have to also minimize or maximize your utility subject to a certain budget constraint. It's okay. The same thing applies to this one, but in this case, they are saying that okay, minimize your portfolio variance subject to a certain constraint, and the constraint is that when you sum up the weight of each of the asset, it should be equal to 1.
Oh, I got it. Thank you. Yeah, I got it. I remember now.
All right. Okay. So look at something here. Now, please, from here, look at it. Please, this is the most important part. So, Richard, are you here?
I'm here.
Okay, great. Okay, so please look at it from this side. This is the most important part of what we are doing today. Now, what we are going to do here now, we have 4 different variables here that we don't know. When you check the question very well, in the question, you have been given your variance of k, you know, right? You've been given your variance of what? H, you know. you've been given your variance of L, you know, or that your standard deviation. But once you've also been given your correlation, it means from that you can get your covariance between the covariances that you have in it. So you know those ones. What we don't know now is our SK, our XH, our XL, and the lambda. Is okay?
Yes.
Yeah, continue. Yeah, continue.
Okay. Please sometimes respond so that I will know that you guys are following. I beg.
Yeah, so you know our audio is muted, that's why.
Oh yeah. Sorry. So what I'm coming to do now in this case is first, because these are the variables that I do not know, that is H, that is K, S, K, X, L, X, H, and then lambda. These are the 4 variables that I don't know. So I'm going to differentiate the Lagrangian in respect to these 4 variables. Is okay? So if I'm going to differentiate, first I will say that lambda respect to SK. So that means I'm differentiating with respect to SK. Now look at something. When I differentiate this with respect to SK, there's K here. So it's going to give me 2 SK variance of K. The first part, right? Now let's check again. There's also a K here. There's also a K in the 4th component, that is this one, right? So when I differentiate that one also with respect to K, I'm going to have plus 2x H covariance of H K. Is okay. Now in the 3rd component too, there's a K there. So plus, this is also going plus 2xL covariance between K and L. Is okay. Now look at something. When I come to the lambda part, there's also K here, minus K here. So that's going to be minus lambda equals to 0.
Sorry, Usay, I have to, but I lost a little bit. So you differentiated which equation? The standard deviation of the portfolio, the variance of the portfolio?
No, when you square a standard deviation, that gives the variance.
No, yeah, I'm saying you differentiating the variance of the portfolio, the one up, or you're differentiating the second one?
I'm differentiating this Lagrangian function. I'm differentiating this function, right? But in this Lagrangian function, I also have this in it. This is the variance of the portfolio, which is also this one here. But because it is long, I cannot write them and write this. That's why I've used this to represent that.
Okay.
Yeah. So when what I'm doing now is I'm differentiating this in respect to K, because the variable that I'm looking for, they are 1, 2, 3, 4. So if I'm differentiating this respect to K, there's already K in this function, which is 1. There's 1 here. There's 1 also here. And there's 1 also here. Right? So I'm differentiating these 3 components with respect to K. Now when I differentiate this, the first component is SK squared. So the 2 will come down. That will give me 2 SK variance of K. It's okay. Now when you look at the second component, there's no K in it, so I don't touch it. When you look at the 3rd component, there's no K in it, so I don't touch it. The 4th component too, there's no K. Now when you come to the 5th component, there's K here. 2SH SK covariance between H and K. So when I differentiate, when I differentiate this with respect to K, now I'm going to have 2SH covariance of HK. Now in the last component for this part too, there's K there. So that gives me 2XL covariance between K and L. Now, so that means I'm done with this first part. Now when I come to this part 2, that's the constraint part, there's also minus SK. So when I differentiate, that will give me minus lambda. then I equate everything to 0. So that is equals to equation 1. Is okay? Please, if there's any question, kindly ask before I continue. Sandra.
Proceed. Sandra understands very well.
Yes.
Sandra, you don't have any more one question?
No, I don't have questions on this.
You don't have one more question, right? That's fine.
It's unlike Sandra.
Okay. Sandra always has one more question, so I wanted to be sure. All right. So the next one that we are going to look at is to differentiate this same Lagrangian function with respect to what? L. So when I do that, I'm going to have in the first component there's no L. In the second component there's no L. It's okay. But in the third, now look at something. And when you are doing these two, the order of arrangement is very, very important. It is very, very important. Look at something. When you look at equation 1, I have 2sk, right? Variance of k plus 2sh. Covariance of hk plus 2sl. Covariance of k and l. Now look at something. So I'm going to differentiate the other one. When I differentiate with respect to L, in the first component, there's no L. In the second component, there's no L. But in the third component, there's L. So when I differentiate, I'm going to have what? 2xl variance of L. Now I'm going to write this under the equation, but I'll make sure that it is also beneath the one that I have L in it. So instead of writing it here, I come and I'll write it here, 2xl variance of L. Is okay. Now the next one, let's look at that. So when I go to the fourth component, I also have L in the fourth component, which is this one. So when I differentiate this, I'm going to have L of 1. I shall have 2sh covariance between H and L, right? So when you come to, I have the sh here. So I'm going to write 2xh covariance between H and L. This is a plus. It's okay. Now let's look at the third component. The fourth component. In the fourth component, I don't have any L in it, so I forget about it. Now in the fifth component, I have K and L. So I'm going to differentiate, and that will give me 2ksk covariance between K and L. That will give me plus 2sk covariance between K and L. Now the next one becomes, when I differentiate s of L, that will be minus lambda equals to 0. It's okay. So that means I've differentiated with respect to sk and sl. Now I'm left with sh. Now let me differentiate with respect to also xh.
I'm sorry, why is the lambda negative?
Which one?
The second equation. The second
because when I differentiate with respect to L, this is minus here.
Okay.
Because minus lambda, which is negative, right? So this one is, I think this one is K.
But when you, when you differentiate with respect to L, the first one, no, with respect to K, there is
the
still
first one
negative
with respect to K, yeah.
But the K did not show in front of the lambda, or is that what is that? Is that negative?
The K did not show in front of the lambda.
No, the negative sign doesn't show in front of the lambda.
It's there. It's negative.
It's not equals to, it's negative, maybe.
Okay, it wasn't very
it's negative. Yeah. Now let's look at the next equation. I'm also going to differentiate with respect to sh, right? So when I'm differentiating with respect to sh, I'm going to have L x h. Now I have sh here, right? So I'm going to have, when I differentiate, I'm going to have 2sh variance of h.
Sorry, Osai, I don't know if it is my screen, but I can't see what you're doing right down there.
Okay, so I think let me
I think it's your screen now for this particular one. I think it's your screen.
Really?
Yeah, I can see it. If you think it's your screen, but also you can.
Okay, no problem. So I'm coming. Let me write it somewhere and then continue to the next page. Don't worry, I'll go to a new page. Don't worry.
Yeah, boss.
Yeah. Okay. All right. So let me do it here. Then after that, I'll copy for you to see. Okay. So look at something. I'm differentiating respect to SH. Now in the first component, there's no SH here, right? But in the second component, there's SH there. So it's going to give me two SH. Please don't worry. When I finish, I'll copy for you to see, but don't worry. So let me write it here.
It's okay. I've adjusted it. It's okay. You can write.
All right.
there.
Okay.
It's okay
So
now.
I'm going to have 2XH and then variance of H.
Standard.
Right. Now the next, so this one there's no H here. When you come here to this H, so you're going to give me 2XL covariance of H and L, right? And this XL is here, so I'm going to write plus 2XL, then covariance of H and L, right? And when you come here to where do we have L again? We have L here. This is going to give me the last component. We have 2SKXL. That will give me 2SK. That's going to give me 2SK and 2SK, and then this covariance between K and L. Is it okay? Now the last part is when I differentiate, it's SH. So when I'm differentiating to what SH, right? So I'm going to have minus lambda, because when I differentiate, I have minus lambda. Minus lambda. Okay, so let me skip that. Okay, let me write it here. So now I have, okay, please, I'm coming. I just want to write it so that I'll move to the next page. 2SK, variance of K, plus 2XH, going between H and L. So between H and K, yeah, plus 2XL, K and L minus lambda equals to 0. And we have 2XK going between K and L plus 2SH, H and L plus 2XL variance of L minus lambda equals to 0. We have 2SK going between K and L plus 2XH variance of H plus 2XL covariance of H and L minus lambda equals 0. All right, okay, so let me go to the next one. Okay, so when I come to the next page, so I'm now going to differentiate respect to L respect to lambda. And that is also going to give me 1 minus SH minus XL minus X, what again, K, is it K? Minus SK equals to 0. Is okay. So we have 4 different equations, right?
I have a question on the third equation.
All right, okay. I'm listening to your question, boss.
Please go to the third equation, the slide on the third equation, on the former slide.
Okay, I'm coming.
Thank you.
I think it's this one. Okay, this one.
Yes, and what the third equation.
Yeah.
LXH. The first element there. Variance. I think it's so. I think it's supposed to be variance K and H.
This one, the first part here.
Yes, the first part.
Okay, let me check. Okay, so we are differentiating with respect to S8K. Okay. We are differentiating respect to H, right? So there's no H here. So when I differentiate, I'm going to have 2 SH variance of H. That's what I have, 2 SH variance of H here. Now there's H in this one. I'm going to give me 2 SH. So we're going to do 2 SL, going between H and L. Now when I come to this part, so it's going to give me, okay, 2 SK covariant between H and K.
H and K, yeah.
Yeah, thank you. Thank you. Thank you. So H and K. All right, okay, so great, thank you. So you're going to give me H and K. All right. Okay, so now we have 4 different equations now, right? Now look at something. In the first equation, we had 2 SK variance of K, right? Plus 2 SH covariance of HK plus 2 XL covariance of K and L minus lambda equals to 0, right? That's what we had. Is okay? Okay, so
yeah,
please,
this is the
from this part,
second differentiation, yes.
No, that is I'm talking about the first differentiation.
Third.
The first one.
Okay.
I'm referring to this one. Okay, so please, what I'm trying to do is I just want to write these 4 equations that we've gotten now in a matrix form. So please follow very well. So I'm starting with this one. After that, I will come to this one, and I will come to this one. Is it okay? So let's go back again. Yeah. So I'm looking at the first equation. So I will have so let's write this matrix here. I just want to put it in the matrix. Just want to put it in the matrix. Want to put it in the matrix. In the matrix. Okay. So in the first equation, we have 2 SK, right? Multiplied by the covariance of what? Multiplied by the variance of K. So that means I'm going to write 2 variance of K. Then I will bring the SK here. After that, I will explain, don't worry. Now, in the second equation, too, I have 2 SH covariance of H and K. So I'm going to write 2 covariance of H and K. Right? Then I'll bring the SH here. Then the next one is 2 variance of K and L. Then I'll bring the XL here. Minus lambda. So I'll bring -1 here, and I'll bring lambda here. And it's equal to 0. So I'll bring the 0 here. So look at something. What I've done is that I'm just trying to write a matrix form of this equation. So when you have matrix, always matrix is the same as what? You multiply your rows, which is this one, by your columns, right? Which is this one. So in that equation that we had, even if I multiply this by this, that should give me the equation back again. So I'm going to have 2 variance of K times SK. Will give me 2 SK variance of K. Is it okay? Plus 2 covariance of H and K multiplied by SH will also give me the same thing back, like we had in the equation, plus now times 2 XL, this will give the same thing back, -1 times lambda, -1 times lambda will give minus lambda. Please, up to this point, is it okay? If there's something I don't understand, ask me from here.
I don't. It's quite confusing because the main equation, the main differentiation is in the other slide, the last slide, and now you're creating a matrix in this slide, so we can't see unless you give us a little time to copy out the differentiation so we can follow.
Okay, then I'll be glad if you can do that in 1 minute so that we can, because I've copied it elsewhere myself.
Or
Okay,
just
1
take a
minute, then
picture.
we'll copy it out.
So yeah, so let me go back so that you can copy, either you copy or you take a pic of it. Yeah. Okay, please. So either you take a pic or you copy it in 1 minute.
Okay.
I can continue.
From my side, yes, you can.
Please, can I continue?
Yeah.
Okay, great. Okay, so I'm here. So if you check from the equation, look at this. The first component, this is SK. So when I multiply 2 variance of K multiplied by SK, that will give me 2 SK variance of K. It's the same as the first component, right? You know, in mathematics, anytime that you're doing metrics, you multiply rows by columns. So this is your row, right? Multiplied by your column, which is what I have here, this one. So this 2 variance of K multiplied by SK will give me 2 SK variance of K, which is the same as the first component in equation 1. 2 covariance of HK multiplied by SH will give me the second component of the second component in equation 1. And the next one is 2x, sorry, so this one is 2XL multiplied by covariance of K and L, right? That will 2XL multiplied by this one will also give me the third component in equation 1. Then minus 1 times lambda also give me minus lambda, which is fourth component in equation 1. Is okay?
Yes.
So what I'm doing basically is just trying to rearrange them by using metrics so that even when you decide to multiply it, you have the same thing back. So that is why I told you guys that the order of arrangement from that point is very important. So let me clear this part. Oh, great. So the same way, when we look at equation 2, that is also going to give us 2 covariance of K and L, then 2 covariance of H and L, 2, so this is K, then 2 the next one is so 2 variants of L. No, I'm coming. Becomes two variants of L, 2 variants of
2 variants of L.
Minus 1. Is okay. Then the next one becomes 2 covariance of H and L. No, I think there's a mistake elsewhere. But
yeah, there is a mistake. I think the second matrix. I think XK has to be
not
second one.
There's a mistake in the second one. Yeah. Let me go back. Let me go back. Let me go back to the second equation. So let's look at the second equation. We differentiate ourselves to what? XL. So first we're going to have 2XL variance of L. All right. And variance of L. SK, SH. So SK, I'm coming. SH. Okay. I think it is not wrong, but I think this one should come first. This one should rather come first. Let's go back and look at it again. I'm coming. So sorry, let me check again. So from here, let me clear this part. Okay. So from here, let me clear this part. So let's see. This is. So the first one is K. The second one is H. The third one is L. Okay, let's look at this. So the second one is and it was the third equation that we had H from. So I'm going to have 2 covariance of H and K. So this one is K, right? 2 covariance of H and K. And then the next one going to be.
The second one.
Come again?
Is this equation the third one or the second one?
This is the third equation because the order that I have is K, okay, H, and L. And it was the third equation that I differentiated to H.
Okay.
Which is this one here. So then 2 variants of H. And then I'll have 2 covariance of H and L. Like this, minus 1. Then this one becomes the second equation, which is that one also becomes 2. It's going to give me 2 covariance of H and K. The next one becomes
H and K.
No, H and K.
No, it becomes. So it becomes the second. I'm working the second equation.
Okay.
Is the second equation now?
Okay. Yeah. Okay.
That's the second equation now. So it comes 2 covariance of K and L. Like this.
Yeah.
And then it comes
H and L.
2 covariance of H and L. And then the next one becomes 2 variance of L minus 1. And that also gives me equals to 0. It's okay. Now the next one is differentiate fourth equation when we differentiate respect to lambda. It's okay. So that one is that is what we had 1 minus SH. We had this one here. So the same as SK plus XL. No, so SK plus SH plus XL equals to 1. Is okay. So that means I have, when I take sk out, I'll have 1 here. I'll have 1 here. I'll have 1 here. And there's no lambda in this equation, so lambda part becomes 0. So KHL lambda is okay. So when you multiply this by K, so what it means is that you multiply this by K, this by H, this by L, this by lambda, it gives you everything back. Okay, so this is what we have. This is the matrix that she got. So we call this matrix, let's call this matrix A. Let's call this one B. And let's call the, so now the way that we don't know, let's call that one X. So I can say that then AX is equals to B. In this case, each of them represents matrix. So the A is matrix. So if I'm looking for X, then I will say that X is equals to A inverse multiplied by B. Is okay. Now look at something here. So what you have here in this case is it consists of the variance covariance matrix. This part here, from here to here, it's just like the variance covariance matrix, but multiplied by 2. Is okay. And then this one is the 1, 1, 1 part. So now what we are going to do now with the question is, we are now going to move from here to Excel. Because you can't solve this equation using the manual way. Or what the TA was also suggesting is that, let me explain that part to you. What she was suggesting the other time is this. When you are able to solve up to this point and you've gotten these equations, 1, 2, 3, plus the last one making 4, then you can decide to solve this equation by making one a subject and you put in this, which is difficult. I know how to solve mathematics by way of substitution. So what you can do is say, in this case, you make SK the subject in this one. Then you come and replace it into equation 2. Whatever you have, you replace it to equation 3. And you replace it into equation 4 before you have your final answer, which is, I don't even think you can finish that within 30 minutes or 40 minutes. You can't.
I think that will take the whole hour, yeah.
Exactly. So now that so my duty for today is just to explain to you what is it? Sorry, I'm coming. So my duty for today is just to explain to you how she was able to get this matrix. So imagine if we had, look at something. So let me add one thing, then we continue. So the one that we had in the one that we had in the bonus exams. That in the bonus exams, we were given 2 constraints. The first constraint was on your weights. That is XA plus SB plus X equals to 1. And the other constraint was you were given a portfolio return that they expect you to have. So if there's also a portfolio return, I will consider that my Lagrangian in this case now becomes L is equals to variance of the portfolio 1, portfolio plus lambda into bracket 1 minus SA minus XA minus XB minus XC minus XC. So I'll call this one lambda 1 plus lambda 2 into brackets. Then I'm going to have the portfolio return, mu of the portfolio that they want me to get, minus XA multiplied by RA. Minus XB multiplied by RB, that's the return on B, minus XC multiplied by return on C. Is okay. So if you have this, now that means imagine if I had now if I had also differentiated respect to RXA, you know, with respect to equation 1. So let me come back to this one again. respect to equation one, this one that I had, I differentiated respect to what? SK. But because there was no constraint 2, I ended it here. So if there was to be a constraint 2, this one would have been minus lambda 1. Then I'll come to plus lambda 2 into brackets. That's the constraint. So when I differentiate, that will give me minus return on A. Minus return on A lambda 2. I don't know if you understand it.
Again.
No, I don't know.
So that's what I'm saying. So far, what I was doing with you guys, we were given only one constraint. It's okay. So that is why I only added that constraint. But in the case of the mock exam that we did, we were given 2 constraints. The first constraint was that when you sum up the weight, it should be equal to 1. That's the constraint 1. And the second constraint was that when we multiply the weight by the respective returns, we should have a certain portfolio returns, which in my case was 20%. And some in other people's case, they were different, right? So what I've done in this case is just this question, we were not given the portfolio return constraint. So I only restricted myself to that of the weight. And I'm saying that in the case where we have portfolio returns attached to it, then in my constraint function, then in the Lagrangian that I set up, which is this one, I would have added plus lambda 2. So let me clear this part. Let me clear everything here. Let me clear these ones.
Also, sorry, what is the term after the lambda 2, the first term from the brackets?
Which one?
In the next slide.
You mean the matrix?
Sorry, not, yeah, where is the matrix? There is lambda 1 and lambda 2, and after the lambda 2, the first term from which you subtract the xa times ra.
I don't. Are you reading from the TA's notes?
No, like
no,
you wrote this thing. I think she's talking about the expected return of the portfolio, like the constraint you're trying to establish.
Yeah, that is why I'm cleaning this part and then redo that part again for you to understand.
Okay, I just don't understand what you write down.
Yeah, that's why I'm cleaning this part so that I will have space and write it here. So you see,
okay.
First, this one that I'm doing with you guys, the constraint is only one, right? Which is the weight. It's okay. So that's why I said 1 minus xh minus xl minus sk should be equal to 1. It was when you add up, it's equal to 1. So I'm just subtracting from the 1. I have this, right? So this is only when you have one constraint, and the constraint is that when you sum up the weight, it should be equal to 1. And what I'm saying is that in the case of the mock exams, we were given what? Portfolio constraint. Now what the portfolio in this case becomes mean return on the portfolio is equals to x of h multiplied by return on h plus.
Yeah, the first sign is mu of portfolio.
Yeah.
Okay. Thank you.
Mu of portfolio is equal to the weight of h plus the return on h plus the weight on k, return on k plus s of l and the return on l is okay. So this counts the portfolio return is okay. Now in the mock in the bonus exams, we were also given a portfolio return. That is also a second constraint. But in the one that I'm solving with the tutorial, we only have the one constraint, which is the weight here. Now what I'm saying is that imagine if we had been given the portfolio return in this case, in the one that we are solving, then I would just have added this becomes lambda 1 plus lambda 2 plus lambda 2 into brackets mu minus. So it becomes this one becomes here. Then it becomes minus this, minus this, minus this, right? So that when I differentiate, so in this case, instead of ending here, that I got when I differentiate respect to x, the first, let's say I differentiate respect to sk, I had 2k variance of k plus 2sh covariance of h and k plus 2sl covariance of k and l minus lambda, because when I differentiate sh, I have only minus 1, which is minus lambda, so it comes minus lambda 1. I would have gone further and differentiated this one respect to what? sh again, that would have given me minus rh lambda 2. Is okay? Please, is okay, please.
Yes, it's okay.
The explanation is okay, right?
Yeah.
So that means in that case, if like the matrix in this matrix 2, it would have been something like this matrix would have been something like, let me clear this part. Here would have been lambda 1, here with lambda 2. Is okay. Then I would have gotten something like minus return on, because I differentiate respect to what? H, return on H. Oh, sorry. It would have been minus return on, let's say, H minus return on, no, this one minus return on K, because I differentiate respect to K. This one would have been minus return on K minus return on H minus return on L, and this one will be 0. Then I come here to the same way that I did when differentiate respect to lambda. I'm going to have also the same thing. RA, I'm also going to have R K R H R L, and I'll have 0 0. It's okay. So when you have two constraints, this is what you get. And when you have one constraint, you only have this part. I don't know if you are getting what I'm trying to say.
Yes, it's clear.
Yes, but there's no shortcut for all of this. I mean, there's any other solution.
So the shortcut for this one is just to know this, that anytime that you are forming your matrix, variance covariance matrix, this matrix, the shortcut is only this. So let me clear this and explain. Let me clear this and write the shortcut here for you, so that you don't always waste your time on that. Okay, so let me go to new page. Okay. Coming. Okay, so the shortcut is this. If I'm the one doing this, this is what I will do. Because now I've explained to you guys how we drive those things. So I will just write this. So when I begin, I will just start. Okay, I'm just going to write here as, I have two portfolios. Let's say I write here as SH. I write here as SK. I write here as XL. Then I'll write here as my mu. And I can even call this one constraint 1. I'll call this one constraint 2. Then I'll come here and write my XH, SK, XL, lambda 1, lambda 2. Okay, so what I will do now here, that I know that, okay, in this case it's going to be 2 variance of H. Here is going to give, I'm looking at, okay, here too is SH. Here is also X key. Here is also XL. So then I know this is also going to be 2 covariance of H and K. This is going to be 2 covariance of H and L. Now, in this case, this is the constraint. I know that this is a constraint. The constraint one is, let's say I'm assuming that constraint one is from the portfolio return. So I know that I'm differentiating only this respect to H. So I'm going to have minus return of H. And this is minus 1 because I differentiate, I have minus 1. Then I'll come again 2 covariance, 2 covariance of H and K. The variant becomes 2 variants of K, and this comes 2 covariance of K and L. I know that I'm differentiating with respect to what? K. So minus return on K minus 1. Then I'll have the same thing applies to this one. I'm going to have 2 covariance of H and L. Then I'll have 2 covariance of K and L. Then going to give me 2 variants of L minus return on L minus 1. Now when I come here to I differentiate with respect to lambda. So when I differentiate with respect to lambda, I'm going to have return on A, return on K, H, return on K, return on L. This is 0. This is 0 because there's no this one in the other part of the lambda. So this is also, and then I'll have 1, 1, 1. Yeah, so 0, 0. So this is the matrix for it. But at least now you know the intuition behind how we are getting these ones, the process that we went through. Now after you've gotten this one, then you also know that when you come to this part, in the first equation, you differentiated respect to what? H, and you equated everything to 0. Right? You equated this one also to 0. You equated this one also to 0. But in the case when you differentiated respect to the lambda 1, if you remember I said lambda 1 was equal to this. It was lambda 1, let's say lambda 1 is equal to mu of the portfolio minus SH RH minus SK RK minus XLRL. So this is only referring to the first constraint part. So the second constraint part becomes plus lambda 2 into bracket 1 minus S of H minus S of K minus S of L. It's okay. So when you differentiate everything here with respect to lambda, it means lambda will vanish. So you have only this one. So when you have this one and you equate this one to 0, you're going to have SH RH plus SL RL plus SK RK plus SL RL equals to mu portfolio. So what it means is that this one, if everything you equate to 0 equals to mu portfolio. So it means here I'm going to have the mu portfolio. And then here too, when I equate differentiate respect to lambda, I'm going to have S1 plus SK plus SL equals to 1. So after the equal sign, what I have here is not 0. It is also 1. So then you have for this. Is it okay?
Yeah, but for the matrix A, how do we get the last row? 1, 1, 1, 0, 0.
Oh, that's what I just explained.
Yeah, I know. I didn't get it. That's why I'm asking you again.
Yeah. So what we are doing is this. For instance, when we differentiate with respect to, you mean the down part or the column part or the row part?
The row part.
The row part. That means this part.
Yes.
Right. Great.
Yes.
So look at something. This is what we have here. Now when after you know we had 5 different now in this case we have 5 different variables: XH, SK, SL, lambda. Oh, sorry. SL, lambda 1, lambda 2, right?
Mm-hmm.
Now, so look at something. Now, when I differentiate respect to lambda 1, it means lambda 1 is going to vanish because this one will vanish, right?
Yes.
So I'll be left with only this equation, right? And I'll equate it to 0, right?
Mm-hmm.
Now, if I equate everything here to 0, then it's the same as sorry, 1 minute. So when I equate everything to 0, it's the same as writing SH plus RH plus SK RK plus XL RL equals to the mean of the portfolio. Is okay. Sandra, are you okay with this one? What I've written?
Yes.
So great. So what I'm doing now is I'm just taking these ones out. So when I take the SH out here, which is here, and I multiply by RH, it will give me the same this thing here.
Okay.
Now when I multiply this expression that I have here, when I multiply RK by SK, it's giving me this thing here. That's why I wrote RK here. Now this expression that I have here, when I multiply this one by SL, it's going to give me this here. But in this equation that I have here, this one that I have here, there's no lambda 1 in it. So in the case of lambda 1 is 0. There's no lambda 2 in it. So in the case of lambda 2 is 0.
Okay. Okay. Yeah, got it. Thank you a lot.
All right, okay. And the same thing applies to when you differentiate with respect to the constraint 2, which is XA plus SB plus XC equals to 1. In that 2, there's no lambda 1, lambda 2 in that 4th and then 5th equation. So that part becomes 0. So basically what I have here is just the same as this one is just like lambda 1 and then lambda 2. It's okay. So, but in equation 1, we had lambda 1 and lambda 2 in it because it was lambda 1 multiplied by h minus lambda 2. That's why it is there. But in the fourth and the 5th equation, there was no lambda. That's why it is 0. It's okay. So the most important thing is being able to write this one. When you write this one here, that becomes this is just your normal variance covariance matrix that has been multiplied by 2. So this shouldn't be a problem at all. Now when you come here to, it becomes if you are dealing with because in the first case it's for h. Look at them, because if you check, look at something, it's variance of h and k, h and l. So it means this line here, this line here is for h. So this one becomes R and H, return on H. The same thing that this one's supposed to be, this is K, so it's ideally supposed to be K and H.
Foster is trying to get inside again, so let him in.
Come again?
Foster is trying to get inside again because it seems that his computer was restarted. So give him the permission to go in.
Okay. Great. So that is what you have in this. Now, if you understand up to this how she was able to metric that in her tutorial she didn't do this one. She only wrote the matrix and she was solving it. Now that we understand how to derive the matrix, I'm now going to shift to Excel. Then we will use the Excel to solve it, because when you have this equation, this matrix is what I think this is 1, 2, 3, 5 by 5 matrix. You cannot solve 5 by 5 matrix using a manual approach. So in this case, we have to use the matrix. So I'm now going to use the matrix to explain to you how she did it. So what I'll do now is I'm going to open my Excel. Okay. So let me open my Excel. Sorry, 1 minute. I'm now on my Excel.
I say, what's happening now?
Yeah, can you see me? Can you see the Excel?
I can't see it.
I'm coming. Let me stop this one. Sorry, 1 minute.
We cannot see the Excel.
Are you sure? Can't you see the Excel here?
No, you have to go to share screen and choose the Excel itself. Choose the
I think
file.
that's what I'm doing. I'm coming. Let me go back to again. Book Excel.
Here we are.
You can see now.
Yes.
Great. Okay, so now I'm coming to use the Excel to do this. Okay. So let's start with let me look at the question again.
So this is the way that you are going to do it anyway in the exam, right?
Yeah, in the main exams, you don't have to use the manual approach. So you just have to know how to use the Excel.
Yes.
Yeah. Okay, so now let's look at the question. We have so let's say I'm going to start with.
Are we solving first the problem from the bonus exam now?
Come again?
Are we solving the first problem from the bonus exam now?
No, we can as well do that one, which is not a problem. But I was looking at solving the problem 2. It's almost the same thing. So when you can as well do that.
Okay.
So let's say correlation matrix. Correlation matrix. So in the correlation matrix, I will call this part K, L, and I will call this part I'll call this part K. Okay, so let's say KH. This one is L. So I'll say KH. and L. So we've been given that no, always correlation for this one is 1. Now correlation between K, said K and H is 0.5. All right, and that of H and L, and H and L, was H and L is negative 0.5. So that means if you have this, this is also H and K, and we have K and L is 0. K and L is 0. K and L is 0. And we have K and H 0.5. And we have this one as this one is 1. This one is 1. This one is negative 0.5. So we have this one, the correlation matrix. So the next thing that we're supposed to look for is we can also get our variance from this. So let's see, but we can, okay, so let's set up the matrix that we are going to use to do it. So with the matrix, you remember we said the same as what? 2 times of the covariance, right? So let's get our covariance variance matrix. Covariance variance matrix. Variance matrix. All right, great. So, and in the question, we know that we've been given, we have K, H, and L. And H has a stock of, so let me say this is their return. And this one is the volatility. And this one is the volatility. So the return here is 20%, which is 0.2, and the volatility is 0.3. And that of H is 0.1. And the return is 0.2. And the same thing for this 0.1 and then 0.2. Great. So I'm looking for the variance covariance matrix for this same thing. So let me see, I will come here and say this is K, H, L. K, H, L. And then we have, so if I'm looking for the variance of K, so variance of K, you know, we've been given correlation metrics, but we know that anytime that you are looking for the covariance, because it's the same as what correlation times the standard volatility of the two, right? So I will say that this one is equals to this one is K and K, so it's going, the correlation for K is equals to this times volatility of K, and again the volatility of K, because yeah. So I'll have this. Now I'm looking at K and L. Now I'm looking at K and H. So K and H is also the same as equals to correlation between K and H, which is 0.25. Shift star K, volatility of K, and the volatility of H. What is this? Great. Now I'm looking for this one too. Is K and L is equals to K and L. The correlation is 0 times K, volatility of K, and then volatility of L, which is 0. So when I come to this, I'm going to have H and K. So H and K is also equals to, H and K is equals to H and K, the same to 0.5, H and K. So this one is the same as this, and this one is the same as equals to 1 times variance of H times variance of H, and this one is equals to this one is H and L is equals to negative 0.5, which is this one, times H and L. Great. Now, so I think in this case is also equals to correlation between K and L is 0, and times the variance of K variance of L is also equals to 0. And the same thing applies to this one, which is equals to H and L. H and L 0.5 times H and then times L. And this one is the same as L. So it equals to this one, shift star, the volatility of L. Okay, so please, this is the variance covariance matrix. If you have any question, please kindly ask before I continue. Can I continue?
Just a minute. I'm trying to. My numbers is a little bit different.
Okay, so this is what I'm doing.
H and H is. I'll just check it.
H and H.
Yes, this is the
okay, so H and H is the formula is correlation for H and H is 1 times the variance of H, which is 0.2. And then L and L. Correlation for L and L is what? That is this it is 1 times the variance of L, which is
no, it's all my numbers are like yours, compatible. Yeah.
They are same?
They are same.
Okay, great. So that means this is what we have as the variance covariance matrix. Now I'm now going to set up the matrix that we are going to use. It's okay. The matrix that we are going to use in finding the weights. So I will say that first is 2 times of covariance of this one, right? So if you remember, we said this equals what? 2 covariance of this one, which is this. This is a covariance. 2 star of this. And this one is also 2 times of this, right? And this one was also equals to 2 times of this. Now you have this. Now when you come here to, it's also equals to 2 times of this equals to 2 times of this, which is equals to 2 times of this equals to 2 times of this equals to 2 times of this and equals to 2 times of this. Okay, so this is the variance covariance part of the minimum variance portfolio that we did, that I differentiated respect to X, H, S, K, S, N, the lambda, if you remember. Right? So this part becomes minus 1, minus 1, minus 1, 0, 1, 1, 1. It's okay. So in this case, now let me call this part X, H, right? So I think the first part is SK. So let me call this part SK, XH,
and then XL. So this is going to be the weight. I'm going to put it here. Now, when we come to the constraint other part, we had equals to 0, 0, I think it was 0 and 1. So I'm going to call this one as metrics from minimization problem. Then I'll call this, so I can, that is, let's say that is matrix A. And I'll also call this one matrix B. So we said X, which is the weight, is equals to A inverse multiplied by the matrix B, right? That's what that is what we said. So that means I will have 1, 2, 3, 4. So I can just come in and say that 1, 2, 3, 4 is equals to matrix inverse of so this is the matrix inverse. I'm just hoping that this is correct. But I hope you are following.
I just lost you in here. Just how did you do this again?
The matrix inverse.
Yeah,
it's just
yeah.
Okay.
Multiply the columns with the row.
So you just, this one is 4 by 4, right?
Yeah.
It's 4 by 4. So you're just going to select 4 by 4 also here. 1, 2, 3, 4. Then bring is equals to. Then matrix. I'm looking for matrix inverse. So you see, it has given matrix inverse.
All right.
So I will select the areas that I have. What is this? I'll close it. Then I'll get Control Shift and Enter. No, I think I selected more than that. Sorry. So I select 4. 1, 2, 3, 4. So equals to matrix inverse Control Shift and Enter. Why am I selecting
5?
I selected 5,
not 4.
It's 5, right? No, it's 4.
You selected 5.
I selected 5. 2, 3, 4. 1, 2, 3, 4. Okay.
Yeah.
Is equals to matrix inverse. So you select where you have this. Control Shift Enter. And that gives you this. So now what I'm looking for in this case.
Right, matrix. You just wrote matrix?
I just look for the matrix inverse.
Okay.
So this is the matrix inverse. Now what I'm now going to do is to multiply the matrix inverse by this matrix.
I think behind the expression at the top, the x equals to inverse of A times B, just beside it, you should write the formula there so it stays there, or like metric inverse, just in case you upload the Excel file, we know what happens there.
You mean this one?
Yeah, just beside.
Okay, but that is the formula he has written, because okay.
Yeah, exactly. Thank you.
If you get A raised to the power minus 1, you should know it's an inverse. Okay, so you want it this way, right?
Yeah.
Okay, fine.
It seems that I have to
okay,
put the function in the Excel. Yeah, it's not there.
Now I'm now looking for the F weight, right? But I have lambda also in it, so I will just say, okay, this side is lambda. Great. So I'll come here and I'll select this 4. Now say it's equals to matrix multiply
the inverse, which is this one, comma, and this one, you close it, Control Shift Enter. I think that there's a problem with this. Let me check first. Because ideally, it's supposed to sum up to 1. Once it's not up to 1, it means there's a problem. Yeah, there's a problem. So let me check this one again. This one is 2 times B15. Okay, so this is, let's do the variance covariance matrix. Yeah, so this is the correlation that we had. And they said if you're looking for variance covariance matrix, it is this one. So you have 0.09 covariance of here. This is 2. This one is B4. B4 is correlation. This times the volatility is 0.3, 0.3 here. I think that's what was given in the question, right? Let me check. 1, 2, 8, 9. Okay, so it was volatility was 30%. Okay, great. Now the next one is also K and H. So the correlation for K and H is C4 times H, which is K and H is 0.82 and 83, which is this one here, correct? Okay, then and how come? And let me look at this one also. So one, this and this and the same thing as this. Now K and L. K and L is also a correlation between K and L is 0. So that means everything will be 0, and here is 0. Now this is also 0.4. This one is also 0.4. So then how come? Because it's supposed to sum up to 1. Was negative. No, come in. So let's check this one again. We had 2 covariance of, where's my pen? The equation is 2 covariance of K and K is variance of K, 2 covariance of K and L, 2 covariance of, 2 covariance of K and L, or K and H, K and H, and then 2 covariance of K and L. That's going to give you 2 covariance of K and H, 2 variance of, so it's going to be 2 H and K. These 2 variants of H, 2 covariance of H and L. They're going to have 2 covariance of this K, H, L, and K, and then 2 covariance of L and H, then 2 variants of L. I'm going to have -1, -1, -1, 1, 1, 1, 0. Yeah. Okay. So this one is matrix. So this one is 2 times of the variance of this, which is this one, and then this is 2 times of covariance of. Yeah, this is the covariance of K and H, which is this one, and 2 times this is 0. This one is 0.06. This one is, so this one is the same as this. 2 times of 6 is 0.4. So then how come? Because I'm coming. When you sum up, it's supposed to be equals to 1, equals to sum of. No, why -1 is supposed to be equals to 1, so there's a problem somewhere. It's supposed to be. I'm coming, let me check and be sure. And then this one is also. Yeah.
You didn't multiply the inverse of A times the matrix of B.
You said I did what?
You didn't multiply times the matrix of B, right?
Yeah, I multiplied the inverse by the matrix of B.
You did that?
Yeah, that's what I did. 0, 0, 0, and then 1. Yeah, so when you check it here, you can see matrix inverse of this, B27 to E30, which is B27 to E30, right? By
J20, yeah.
Yeah. So that is this one. I don't know why I'm getting. I'm coming. So let me try with my. I have something. So let me try with what I have here. Okay. So no problem. Let me try with what I have. I'm coming. 1 minute. Okay. So desktop. Okay, so let's try with this one. Okay. Okay, so yeah, so great. So the return is almost the same thing. So I don't know why I'm not getting it here. Okay, so let me compare what I have here. So variance covariance, I have 0.09. Variance covariance matrix. No, I don't need this one. 0.09, 0.03. Oh, so no, hold on. This one is not 0. So I'm coming. Let me look at this. Also, we're looking at the same thing.
You're not sharing the Excel sheet.
Oh, sorry. Oh, sorry.
No worries.
You can see now, right?
Not yet. Yeah, now I see it.
Okay, so I'm looking at the same thing here. So the variance 0.5. No, so hold on. It's okay. It's H, K, and L. That's how I did it here. H is H, K, and L. All right. So then how come I'm coming? And then 0, there was, yeah. So let me look at the variance covariance matrix. I want to compare this one and see. Variance covariance matrix. That is what I have 0.03, 0.09. Okay. 0.04. It's almost the same thing. But matrix inverse matrix representation. So this matrix representation is what? H. So in this case, I made it HKL. So let me look at what I had here. So 0.18, 0.06, negative 0.06. Where's my negative 0.06? Oh, negative. So how come I didn't
We
get?
don't have negative 0.06.
That's what you got, right?
No, I don't have it.
So I'm coming, negative 0.06.
Which one? Because there's two, there's
two times
0.06.
I'm coming 2 times D8, D18. Yeah. So it's okay. So no problem. Let me use the same thing here. Okay. So look at something. So let me use, but I think it's the same thing. I will have to work on that again. So in H, they said the volatility is equal to what? 0.2, right? So they said the return on H is 0.2. Is okay. And the volatility is 0.3. 30% is here, right? And K is equals to 0.1. It's here. And L is equals to 0.2. So that's 0.2. This one is 0.2. So what I did here was variance covariance matrix. This is one. This one was 1. This one was all these ones were given. So we did not need to. So let's do it again. So we have H. So let me start with this one here. H. Okay, so let me share the screen. I don't want to use this. I want you guys to follow. So sorry. New share. So let me share the screen again. So H. Okay. I don't want to use what I have there because that will make it difficult for you guys to understand. H, K, L. Okay, so what? Okay, all right. So the correlation matrix. Now we are saying that H is equals to, in the question we said 1, 2, 8, 9. So the correlation between H and H is 1. Then the question was said that H and K was 0.5. H and K was 0.5. H and K 0.5. H is 0.5. And then H and L has negative 0.5. And H and L negative 0.5. H and L negative 0.5. And that of coming H and L is negative 0.5. So that means H and K is 0.5. This is 1. And this one is supposed to be K and L is 0. K and L is 0. So K and L is 0. And then this K and L here 0. Right? And then we have this one to be H and L negative 0.5. It's okay. All right, so now we have this here 0.5, 0.5. Now let's come to this part. Now we are saying that this is the same as variance of K is equals to variance of, so let me start here as H.
Yes.
So let me make the A is equals to H, K, and L. So H, K, and L. All right, so H, K, and L. So I have H is equals to, variance of H is equals to this times variance of H is this. And then this one is variance of, let me look at the variance of L is equals to, this one is 1 times, this one is L, and times another L. And then let me come to L, and L is equals to 1 times variance of L, which is 0.2. No, but what? Why? So they can't all be 0.04 because one is, this one is K. Where is K? So K is equals to, variance of K is equals to this.
Kusai, you have to put the volatility as well on the same sequence, HKL.
Yeah,
so,
yeah, that's what I'm trying.
Not going to get, we're not going to get confused.
So exactly, that is what I want to do now. So that means this one and this one, they are the same, and this one they are now the same. This and this are the same. Okay, great. Now, so let me see. This is H and L. So H and L. So what the correlation between H and L is negative 0.5. H and L is negative 0.5 times H is here times L is here. No, why am I making the mistake? This H. Okay, guys, let me use what I've done. So it's the same, but so let me use what I've done to explain. So later on, maybe you can do that. So this, let me use this one here. So this is the amount involved with 25,000. And this is the volatility. Return on H is 0.2. Volatility is 0.3. Return on K is equals to 0.1. Volatility is equals to 0.2. And this in order. Now, correlation matrix was given already. So that's what I've done here. It was given. So just H and K, L, H, K, and L. Now, let's look at
I know the mistake. Where is the mistake?
Okay.
Yeah, the mistake that you had put the volatility of K 0.3.
But what was it?
And the other Excel sheet.
Is it not 0.3?
It's H 0.3. As per this Excel sheet.
Okay, fine. But I hope you can follow what I'm doing now, because I think there's no more time, so I think you can follow what I'm doing.
Yeah,
right?
exactly. Yes, because
yeah. So let me explain what I'm doing. Okay. So that is it now. So you have this. So oh, sorry, I want to explain what I'm using, the one the correct one. So what is it? I hope you can see this one, the one in red.
Yeah.
All right. So great. So now when you look at the variance covariance matrix, the formula is what? Correlation of B11. B11 is what? There's the same thing. 1 times C5. What is C5? What is C5? Exactly. Volatility of H times C5 all squared. That is red. So it's almost the same thing. So when you come here to is variance, the variance of K, which is the same as C12. C12 in this case is the same as the correlation between K and K, which is 1 times that times the volatility of K twice. Volatility of K is 0.2, which is C6. C6 is twice. Great. So that's what I did here. Now let's come to the matrix representation of the portfolio, which that's what I was trying to do. Now they said this is the same as well, 2 times of the covariance, right? Which is 2 times 0.18, which is 18. 0.18 is okay. You know, we said when we did the minimization, we came to the conclusion that in writing your matrix representation is 2 times the covariance of whatever you have in the variance covariance matrix. Hello?
Okay.
Right, so that's what I'm doing now. So 2 times of the variance covariance. So you can see this 2 times of this is giving 0.18. 2 times of this giving 0.06. 2 times of this giving 0.03, right? So that's what I've done for everything here. Then I'm just adding the constraint, -1, 1, 1. It's okay. So until I think the mistake.
But can you please, Kuzey, tell me how you make the matrix again? You selected the area that you want to put the numbers in it. Then
Yeah,
you
so
write
that's what this is what you have to do. Okay, so I can't work in the one that I have here. So okay, so let's see.
Yeah, because actually I'm trying to do it. It's not happening with me.
Yeah.
Maybe I think you should just check the correlation he just mentioned, like for H and K, and see if you made a mistake. Because if it is a case, if you change them, everything will be okay.
Yeah, but
yeah, I had wanted to do that, but because there's maybe we spend my time, so I wanted to just use this one to explain. Possibly we thought of doing 2 hours and we've done more than that, so maybe people want to do other things.
Because I think it would have been easier to just keep on following the other one.
Okay, so all right, fine. Okay, so let's do that and let's do that and close. Okay, so now let's do with this. Okay, great. So we can do this one, then we close for the day. So let's start again. The return on K. Let me clear everything here. Let me clear everything. Let me start over so that let me clear everything.
Why, man? Just show the
No,
steps.
no.
You don't have to clear everything and do it again, Jose.
No.
Show the steps and then we practice it.
So that's exactly what I'm doing. So this first, write your return and volatility, which is this one. That's what I've done here. Right there. Yeah. That's the first that you're supposed to do. Now the second that you're supposed to do is to know your correlation matrix, and that was given. That is said, and you know correlation between a variable and itself is 1. It's okay.
That's given.
That is given. Yeah. So once you have this, now the next one becomes find the variance covariance matrix. And variance covariance matrix, anytime you have correlation, and if you're looking for the variance, the same as what? The correlation multiplied by the standard, multiplied by the volatility of the item involved, right? But in this case, because it's H and itself, becomes correlation of that, which is B4, which is 1, times the volatility of H times the volatility of H. Is okay?
Yes.
Great. Now, once you have that, you come to this part. So if you are able to, we are looking for the matrix representation of the problem. And we said it is 2 times of the variance covariance matrix together with the constraint. It's okay. So that is why I have 2 times of the variance covariance, 2 times of this, 2 times of this. So you can see that everything here has been multiplied by 2. Everything here has been multiplied by 2 if you check. That is what I have here. That is this one. It's okay.
Yes.
Then I'm just adding the constraint. When we differentiate, we had a constraint attached to it. So imagine if we had a portfolio constraint, a return constraint that would have also added it to this one. That would have come here, right? Now, once you do that, the next step is to find your matrix inverse. So the matrix inverse is what you just, let's say I need matrix inverse this one. So it becomes equals to, so I will select the area that I want, which is, there are 4, right? So this is 1, 2, 4. So it's equals to matrix inverse, which is I select the matrix inverse. Then I'll select the area that I want to find the inverse, which is this one. Now just control shift.
You're pressing control at the same time?
Yeah, control shift and enter at the same time.
Ah, okay.
Yeah. And so once you do that, you have this. Now, if you have this, then you are looking for A inverse multiplied by this. So it comes, maybe this is what I'm looking for. I'll just come in and select the one that I'm interested in. Here is equals to, then come matrix multiply. Then I will select the one that I want to multiply with the inverse matrix, which is this one. Then you bring your comma, and then you select the matrix B that you want to multiply with, which is this one. Then the same thing, control shift and enter, and that gives you this. So ideally, when you sum up, you're supposed to have 1, but it's supposed to have 1, which is sum equals to.
I think it will go.
Supposed to get 1, which is this. So it is 1, yeah. But I will have to check again to see if it's correct. But that is how it's supposed to get 1. So that means this represents the lambda, and this represents the share in H in K. That means they shorten H.
Yeah.
It's okay. Yeah. They shorten H. That is what it means.
The
now,
mistake you did last time, Osai, was you equate you made like equals to negative matrix inverse multiplied by the B. That's why the weight was wrong.
You said the first one that I did?
Yeah, you did like equals to sign, like equals to negative the matrix inverse times the B.
So I draw negative.
Yeah, that's why it was wrong.
So okay,
so
now you have this. That. So now you have now this become the weight. It's okay, so this now become the weight.
The weight of which stock in the portfolio.
Yeah, that is the weight. Now, if you are looking for I didn't let me check. If you are looking for the variance to is equals to, I think I think transpose of, yeah. Okay, I just want to check transpose of this one. So, and then this is a variance covariance matrix. I just want to be sure. If not, I will check again. Transpose of this and then multiply by this again. No, this argument is wrong. I'm coming. Let me check. I want to be sure. Okay, so multiplicate transpose. Okay, so I think it's transpose. Transpose, comma P18, comma P18. Okay. I think Okay, I think then come here. Control Shift Enter. Okay, great. So now this becomes the volatility. It's okay. So this is the command matrix multiply. Then you bracket multiple matrix multiply transpose. When I say transpose, what I mean is transpose this one. You know the weights. You see A20 to A22, which is this one. Because if you are looking for the variance, you always transpose it. You transpose the weights, multiply by the variance covariance variance covariance matrix times the weight again. So that's what I'm doing here. So I'm saying that just multiply the transpose of A20, A22, and this is the transpose. This is A20, A22. So when I say the transpose, it's now telling it, right? Then multiply by yes.
So by this transpose, we bring the variance of the portfolio?
Yeah, that is going to give the variance. So I just multiplying the transpose of the weight, which is this one, by the B15, D17, which is the variance covariance matrix, which is this one, and then multiply by this one again. So that will give you the variance of the portfolio. So if I want the volatility, it just becomes this one with the power 0.5. And then you have this as 8.2%. That is if every information is right. So in this case, if you understand this, this shouldn't take you more than 10 minutes. 10 minutes is even too long. 5 minutes, you just, all that you need is to get this information correct. Get this information correct. Then get your variance covariance matrix, which I use the formula that when you're looking for the variance covariance, it's the same as what? The covariance is the same as correlation times the standard deviation of the two assets involved. The same that I used to do this. Now, once you know this, you set up your this. You know that this is 2 times of what you have here, together with the constraint. Then you set up your constraint, your matrix problem function. Once you set it up, finding the inverse Excel does that for you. Once you know your inverse, when you multiply the inverse by this, that is the weight. And then you just use this one to get your variance covariance matrix. It's very simple.
So.
Yeah, and in the case there's a constraint. Okay, so Sandra, is Sandra still here?
Yes, I'm here.
Okay, so let's solve. I'm not going to let's solve your exam bonus. I'm going to explain the exam bonus. The bonus exams, the one that we had a constraint.
Okay, but here in this example, the weights are not true.
Come again?
Here the weights, the X, K, X, H, and XL are not. This is the not formula for them. I think this is the right formula, or no?
It was breaking. My network is not good, so if you can repeat it.
Yes, this is the right formula. Here in the cell H22, it's the right formula
for Excel.
Yes.
Yeah, that's the right formula. Yeah.
Yeah. Okay.
It's the right formula. So as long as you have the information in the variance covariance, everything correct, you get the correct answer. But the formula is correct. Okay. All the formula.
Yeah, because I don't understand why you write the formula from G29.
From the formula from what?
G29. It's a formula there.
For which one?
Not H, G. Yes, here.
This one?
Yeah.
From G29. Okay.
Yeah. Why you?
I'm just looking for the variance, and I needed a place to write it, so I could have written it in this place, but I decided this area.
Okay.
Yeah. So I just issued my command there. That is all.
Okay.
I think maybe the answer there, just write it variance, so someone that sees it will know it's variance.
Yeah, you can decide to do it anyway. So Sandra, please, if you have your bonus question, the one that they have constraint, let me explain that with the Excel. I'm not going to do that, and then we end.
Yes, please.
Yeah.
Mm-hmm.
So this is a 3 assets.
Because time is running, guys.
Yeah,
It's been like 4 hours, right?
More than 2 minutes. I'll finish in 2 minutes. Sorry.
No, it's not. It's our problem.
Yeah.
Okay, we are afraid about too much time, you know.
I'll say.
Yeah.
In In determining the weights, I think there is another way by which you can use the Excel. We have something we call the solver.
Yeah, she did mention of the solver, but I didn't know.
Yeah, because I have used the solver in trying to determine the weights and be able to come up with a similar solution before.
Yeah, I think
and
the solver
one
is simple if you know how to use the solver.
Yes, that one is far simpler than this.
Yeah, if you know how to use the solver, it will be easier. But so maybe you maybe in our next meeting you can explain the solver to.
Okay.
Yeah, you can explain the solver to them. Yeah. So Sandra, so look at
yes,
something. I hope you can see my Excel, right?
Yes.
So great. In the this is what was given to in my case in exams. So this is auto mass marking kinky, right?
Yeah.
And this is the variance covariance matrix. Right, this is the correlation that was given to me, and the amount was 25,000. So this is their return and the volatility. It's okay. So this is their correlation metric. So if I'm looking for the variance, it's just the same formula that I used. The same thing in this case is K12 times L6 times L6, which is standard deviation times the correlation. That's what I've done here. Is okay. Now the most important thing is trying to come up with this one, the matrix representation of the portfolio, which is this one. So what we did here was I first write the 2 times the variance of the covariance matrix, which is this one, which represent these ones. Which represent these ones. Is okay?
Yes.
Which represent this one. Now, the constraint is, I'm looking at in this situation whereby you have only one constraint, which is only the weight, right? And then you have it like this. But in the case that you have 2 constraints too, you know, that is in the one that we did. So what is it? So the weight, I'm coming. It's supposed to be So yeah, so great. So this is the variance covariance matrix for the 3, which is this one is okay. So H, K, and L. I'm just using the example auto, masma, and kinky, which has been multiplied by the 2. I'm setting out the matrix constraint. So always multiply is 2 times the variance covariance. So 2 times 0.01 is 0.02 times this is this, right? And this is the portfolio constraint, right? They said the returns were one was 0.25, 0.09, 0.3, which is here. If you check, they are here. What is the return? 0.25, 0.9, 0.3. Is okay?
Yes, and why it's with minus?
Because when we did the differentiation, when you differentiate, you have it in negative. If you remember.
Yeah.
Plus lambda negative.
Yes.
Yeah, so that's why it is minus here. And the other side was also the down part when equation 4 and equation 5, they were positive.
Okay.
It's okay. And after when we equated everything to 0, equation 1 we had is everything equals 0. Equation 2, everything was equal to 0. Equation 3 was equal to 0. But in the constraint one, when I sum up, everything should be equal to the portfolio return. Is okay.
What is this matrix B? Okay. So this is 0.
After I equate everything to 0, I also got a matrix B.
Yeah, and this 0.2 is what?
Is the portfolio return. In my case, we were given a constraint that is supposed to have a return, but in my case, it was 0.2.
Okay.
Right, but in your case, I don't know what your portfolio return was in your case.
It was the same, I think, for all of them.
It was different. It was different. It wasn't the same. Yeah, so that is it. So once you have this, then I just look for my matrix inverse, just like I did. So the same formula, matrix inverse equals to this. Now, if I'm looking for the weight is multiply the matrix inverse by the matrix B, which is on. That's what I've done here. And I have this. And this one is just giving me multiply it by the 25,000, and I know the share in each of them. So if I'm looking for the variance, it's also the same thing, using the formula that I did in the first one, which is also the same as this one. The same thing. And then when I square root it, I have the volatility. The same thing.
So you then check the matrix inverse with the function M inverse. Then you calculate the weight.
Exactly. So when you multiply the inverse by the matrix B, that gives you the weight.
Yeah, but what is in the column M37?
M37.
Yes.
This one.
M.
This is M37.
The next one then.
No, this one is after getting the weight. We were given 25,000. So I wanted to know the amount that I invested in Auto. That is all. So I multiplied it by the 25,000. It says out of this I was investing 15,000.
Okay.
Yeah, and I was investing 8,000 here, 16,006 here. So when I sum up, I have my 25,000 again.
Okay, thank you.
Yeah.
And then the
may I ask a question?
Okay.
If we kept this Excel sheet, I mean, if we have the formulas in our Excel sheet, we just feed the numbers.
Of course, you can decide to do that.
Yeah, right.
Yeah.
Okay, that's good to know.
So you can decide to, because at the end of the day, you're not going to solve anything there. You just write the answer just like we did in the bonus exams.
Yeah, exactly.
If you're able to code, do your Excel in it, you can just decide to. It's just about knowing what you are doing, because even if you have this Excel thing and you don't know what it's about, you can't do it.
Yeah. I mean, like we just formulated better than formulating our formula sheet.
Yeah. That is it. So in the case of, I don't know if but the bonus exams wasn't the same. The only difference was the portfolio return. So if somebody has that, if somebody remembers their portfolio return, I can just change it and we can get exactly the same thing that you have in your bonus exams.
I have 17%.
You have what?
Mine was 17%.
0.17. Okay. All right. So what was your portfolio variance? It was 0.0631 volatility.
Okay.
If you check
what is the formula for the minimum variance portfolio? Can you put in that cell?
No, that is what I've done already.
No, here the L44 it seems to be.
You mean the minimum variance what?
Yes, this one. This one. L44.
L44?
Yeah.
L44.
L47.
47. Which is this one? Also, I said it's multiple matrix multiply bracket matrix multiply transpose of. So look at the transpose of L38 L40. What is L38 L40? L38 40 is this one. That represents the weight. But then that I'm transposing it, because when you check the lecture slide, she said transpose of the weight multiplied by the variance of the variance covariance matrix times the weight again. So this here that you see that L38, L40 is just talking about these three, right? Times K19M21. What is K19M21? K19M21. So look, K19 is here, right? K19 is here. So M21, that represents this one. And this also represents the variance covariance matrix. So whatever I've done here is I'm just using the formula in the lecture notes to do that.
Yes, and this variance covariance matrix is not multiplied by 2.
It's not, no, this one is not multiplied by 2. The one multiplied by 2 was just to get the inverse and the weight. So once you're done, you don't use that again.
Okay.
Yeah.
Okay, and okay, and about the next, the how it was L48, I guess for the volatility. Yes, here.
And then L38, L48 is just about the weight again, but not a transpose.
The volatility, where is the next cell?
This one is just the standard deviation of the standard root of this one. Oh, sorry, the square root of this one gives you the volatility.
Okay. The square, okay, the variance. Thank you a lot.
Right. So when you check your exams, you have, I think when you check the correction, you have 0.0631.
Bye.
I will check it.
Okay, so guys, if if there's no more question, we can end it here. I think that the most difficult part of this one is just this. So in the next, I think the other ones are a bit similar to what we've done. So when in the next time that we meet, we solve problem set 4. We look at 4 and 5 because this one took most of our time. So we look at 4 and 5 and we move to tutorial 2.
But can we solve some problems with solver that we did? It seems like it can come in the exam.
Okay, so with a solver, I'm sure Foster can look at that for us. So maybe in our next meeting, he can also look at.
I will need to go over what I did. I think last 2 or 3 years, but I think in our next meeting I should be okay.
All right. Okay. So
for
maybe
about 10
in
or
our next
15
meeting,
minutes.
Foster is going to look at that for us.
Yes, it will be great. Thank you.
Yeah. Because I didn't. For now, when we are, if you are going to have anything on three portfolio, then you need Excel. You can never do it with the manual approach. It won't work.
Yeah, I'm thinking about like setting up my Excel sheet and just fill up the.
Yeah, I think you can do that.
Numbers and you know.
You can do
so that will be better than. You know?
Yeah, I think that will be better.
Yeah.
Yeah.
All right.
Okay.
It's really helpful, Usai, really. So when are you planning to meet again, guys?
I think it is going to depend on the day that you agree. So once they post on the platform that this is the day that they want us to meet, we will. And when we meet, we look at problem set 4, we look at problem 4, 5, and we look at tutorial 2. Yeah.
Okay.
I think even when it comes to the one on the credit risk, it will be better if you use Excel. That will help because with that part, if not Excel, you can't. Then you can never finish your exams.
Yeah.
Yeah. So we will look at that also. Yeah. So guys.
All right.
Thank you very much.
Thank you, Usai. Thank you.
You're
Thank you,
welcome.
Sandra.
And also
Thank
thanks.
you, everyone.
You're welcome, guys.
Thank you.
See you guys. Hope that you are safe, all of you.
Come again?
Hope that you are all safe. I mean,
yeah, we are safe. We are safe.
Yeah, Sam, we are all safe. Sam, how are you?
I'm doing fine. Yeah, things I'm trying.
Oh, I see.
Thanks anyway for asking.
Osai, when would you upload the recorded video?
I'll make it available. So once once it's done, I will let you know so that you can have it. Don't worry, I'll make it available. Okay. All right, guys.
Thank you very much.
Okay, so
Bye. Thank you.
Bye, guys. Bye.
Yeah,